subject of PPE was discussed in a previous video. In this video, we will provide additional insights into PPE and remind you of some key safety points. Recall, PPE, personal protective equipment, is clothing or devices worn to help isolate a person from direct exposure to a hazardous material or situation. PPE reduces or eliminates the risk of injury by interrupting the route of entry of hazardous materials into the body. Recommended personal protective equipment for a particular material is often listed in its safety data sheet. Recall, this is dealt with in Section 8. Remember to carefully read the PPE section and review your current practices to ensure they are in line with the advice. Now, the use of PPE is the least preferred method of protection from hazardous exposures, as it can be unreliable, and if it fails, the person can be left completely unprotected. Sometimes, PPE may be needed along with engineering controls. For example, a ventilation system, which is an engineering control, reduces the inhalation hazard of a material, while gloves and coveralls reduce skin contact. Use of personal protective equipment may be vital, but it is nevertheless the last and weakest layer of protection. So please keep the safety point in mind. Personal protective equipment should not be a substitute for proper engineering and administrative control, and should be used only where other control methods are not yet effective or are inadequate. However, having said that, PPE can be an important means of protection when engineering controls are not practical. For example, during an emergency or other temporary conditions such as maintenance operations. This section contains basic product properties and incident accounts of some hazardous substances commonly handled in oil refineries and chemical plants. The basic product properties provided here are for reference only, and they are by no means complete. Please refer to the detailed safety data sheets provided by your manufacturers for more information relating to the chemicals at your facility. In addition to the detailed safety data sheets available at your plant, other documentation requirements of hazardous substances include product label, which indicates compliance with standard, and lists items that are part of preparation. Certification organization mark, including technical data package and detailed descriptions of PPE, materials and accessories, as well as technical data demonstrating compliance and user instructions. Now, the hazardous chemicals that will be discussed in this section are now shown on screen. For each substance, we will discuss its properties, exposure limits, symptoms of exposure, health effects, protection from exposure, PPE requirements, and what to do in case of exposure, leak, or fire. In addition, we will provide numerous real-life accident examples. So please feel free to share what you will learn here with others, since this is one of the most effective means of communicating lessons learned and avoiding safety incidents in the future. The first hazardous substance that we will cover is hydrogen sulfide. So if you are ready, then please proceed to the next video to find out more about this silent killer. Hydrogen sulfide is a substance found in many workplaces. The following table shows the sectors where this material may be present. Now, many incidents involving hydrogen sulfide have occurred at oil installations over the years. Among the issues associated with these incidents are inadequate isolation, inadequate purging, plugged lines or equipment, violation of work permit requirements, difficulties in performing job wearing PPE, leaks from valves, pumps, compressors, and other process equipment, desorption from materials such as crude oil, molecular sieves, and so on, and absence of hazard assessments. However, the most common factor in these incidents is the failure to wear proper breathing apparatus. In this next table, we have summarized the most important properties and characteristics of hydrogen sulfide. The focus here is on safety. Keep in mind, hydrogen sulfide can be an invisible, silent killer if safe work practices are not followed. You can work safely in areas with the potential of this dangerous gas by following your organization's hydrogen sulfide contingency plan, knowing how and when to use respiratory protection, and knowing the meaning of your facility's hydrogen sulfide warning sounds and signals. Examples of warning signals are now shown on screen. In this section, we will review 3 key issues and many other precautions that will protect you from hydrogen sulfide exposures when followed. Topics include characteristics of hydrogen sulfide, symptoms of hydrogen sulfide exposure limits, use of respiratory protection, confined space entry, warning devices and monitoring systems, evacuation procedures, and safety tips for working in hydrogen sulfide prone areas. But before to move on to the next video, let me first emphasize this one more time. Hydrogen sulfide is a deadly substance found in many workplaces. Understanding and controlling the hazards it presents is literally a matter of life and death. Your organization's hydrogen sulfide contingency plan contains detailed information designed to control the hazards of hydrogen sulfide. Included in this plan will be a description of engineering controls, worker training requirements, protective equipment, gas monitoring devices and procedures, safe work practices and emergency evacuation and rescue plans, all designed to keep you safe from the harmful effects of hydrogen sulfide. You should always remember the most important aspect of hydrogen sulfide safety is to take your training seriously and maintain a commitment to your own safety at all times. Hydrogen sulfide is a highly toxic, colorless gas that is heavier than air. Because it is heavier than air, it will settle into low-lying areas, creating a hazard if left unprotected. Hydrogen sulfide is formed when 2 hydrogen atoms bond to an atom of sulfur, as depicted here. The chemical expression for this is H2S. H2S is another name for hydrogen sulfide. Besides H2S, hydrogen sulfide is also known as dihydrogen sulfide, hydrosulfuric acid, as well as nicknames such as rotten egg gas, swamp gas, devil's breath, and stink damp, just to name a few. At low concentrations, hydrogen sulfide has an unpleasant odor, similar to rotten eggs. As concentrations increase, its smell may turn very sweet, but you can never depend on detecting this odor for your safety. One reason hydrogen sulfide is so dangerous is that it can paralyze your sense of smell. This is called olfactory fatigue, and it can occur very rapidly, especially at higher concentrations, typically above 100 ppm. Without proper air monitoring equipment, you may be unaware you are being exposed to hydrogen sulfide. Now, it is important to keep in mind here that hydrogen sulfide is found in nature as a byproduct of decomposing organic matter. It often develops in oxygen-depleted environments such as swamps and polluted waters. Hydrogen sulfide can also occur naturally as a component in natural gas, volcanic gases, sulfur deposits, and petroleum. This is why protecting workers from hydrogen sulfide is so critical to safe petrochemical, refining, and drilling operations. Concentrations of hydrogen sulfide are measured in parts per million, ppm. Recall, this is a measurement of how many molecules of hydrogen sulfide are present for every million molecules of air. The inhalation of hydrogen sulfide gas is the most common method of exposure. The following table summarizes short-term symptoms and effects of hydrogen sulfide. At concentration levels up to 10 parts per million, exposed workers may experience irritation of the eyes, nose, and throat. Extended exposure over several hours can result in what is called gas eyes or sore eyes, with symptoms of burning, scratchiness, and tearing. As hydrogen sulfide concentrations increase to between 10 and 50 ppm, exposed workers may begin to experience headaches, dizziness, and coughing. Nausea and vomiting may also occur at these concentrations. Exposure at levels between 50 and 100 ppm can result in the onset of conjunctivitis and respiratory tract irritation after a 1-hour exposure. Conjunctivitis is the irritation and swelling of the membrane of the eyelids, which results in intense tearing, blurring of vision, light sensitivity, and gritty, scratchy feeling. 100 parts per million is also the IDLH level for hydrogen sulfide. This level is the level at which you may suffer immediate, serious, and irreversible damage from exposure. As a reminder, IDLH stands for immediate danger to life and health. Exposure at this level can lead to a loss of the sense of smell within 2 minutes, and altered respiration can occur after 15 minutes. These symptoms will worsen with length of exposure. As concentration levels reach 500 to 700 ppm, an exposed worker can lose consciousness and die in 30 to 60 minutes if not removed to fresh air and given proper medical treatment. When exposed to concentrations of hydrogen sulfide over 700 ppm, unconsciousness can be very rapid, and death will occur in a matter of minutes. Hydrogen sulfide is classified as a chemical asphyxiant. Chemical asphyxiants reduce the body's ability to absorb, transport, or utilize inhaled oxygen. Overexposure causes death through biological suffocation. Hydrogen sulfide in the bloodstream also affects the nervous system, and at high concentrations can affect muscles coordination and the portion of our brain that controls breathing. After small to moderate levels of exposure, persons removed to fresh air normally recover with no lasting effects. However, eye irritation and pain may persist for several days. Keep in mind that the various symptoms of exposure and the speed of their onset can be affected by factors such as frequency of exposure, body mass, overall physical condition, age, and the influence of drugs and alcohol. Once hydrogen sulfide concentrations reach the permissible exposure limit defined in your facility's contingency plan, action must be taken to reduce employees' exposure. When possible, implementing engineering controls is always the first choice to reduce employee exposure to hydrogen sulfide. For example, a work area may be enclosed to maintain a safe atmosphere. Or ventilation systems may be installed to maintain hydrogen sulfide concentrations at safe levels. Hydrogen sulfide gas may also be collected and burned or flared, as depicted in this example. If you cannot reduce the concentration of hydrogen sulfide to less than the permissible exposure limit, exposed workers will be required to wear respiratory protection. For concentrations of hydrogen sulfide below the IDLH level of 100 ppm, a full-face air purifying respirator with chemical cartridges rated for hydrogen sulfide may be used. For concentrations above 100 ppm, or when entering an area of unknown concentration levels, an SCBA or ASR is required, as highlighted here. SCBA stands for Self-Contained Breathing Apparatus and requires that the user carry a limited air supply on their back. SAR stands for Supplied Air Respirator. This type of respirator utilizes purified air supplied from a hose connected to a compressor. If you may be required to wear a respirator or breathing apparatus, then you must undergo a medical evaluation by a licensed physician who will determine your ability to wear a respirator effectively. Annual fit testing is also required to ensure that you can achieve a proper fit in the type of respirator you may be asked to wear. If you may be required to wear a respirator, you will receive specific training on the types of respirators used at your facility, their locations, and the specific situations which require their use. When donning a respirator, a proper seal between the facepiece and your face must be established for the respirator to function properly. A user seal check must be performed each time you put on a respirator to ensure a good seal has been established. When using a chemical cartridge respirator, be aware that each cartridge is designed for a specific chemical. For example, you must have the correct cartridge for hydrogen sulfide for your respirator to be effective. Also, be aware that each chemical cartridge has a usable service life. Cartridges must be changed out before the end of their service life to prevent breakthrough. Breakthrough occurs when the cartridge is no longer effective and the user is exposed to the chemical. This can be particularly dangerous in a hydrogen sulfide environment, since the user may be unable to detect that exposure has occurred. A traditional SCBA will have a 30-minute air supply. It may be used for normal work in hydrogen sulfide areas or for rescue operations. A low air alarm will sound when 25% of the air supply remains. When this occurs, you must leave the area immediately. Now, be aware that some SCBAs are designed for escape only and only have a 5-minute air supply. These are only to be used for an escape and must not be used for normal work or rescue. Some types of supplied air respirators also have a secondary air tank to be used for escape. Again, only use this air supply to escape. Do not use it for regular work or rescue. If you have any questions regarding the respiratory equipment you may be required to use or have any doubts about your ability to use it properly, don't hesitate to ask your supervisor for assistance. Please keep this in mind, your life may one day depend on the proper use of respiratory protection. Hydrogen sulfide is often present in confined spaces such as manholes, pits, sewers, and vessels. Because hydrogen sulfide is heavier than air, it will settle to the bottom of these types of spaces. Unprotected workers who enter such spaces often reach the bottom and then are overcome by hydrogen sulfide and are unable to escape. To make matters worse, this type of situation often leads to multiple fatalities, as other unprotected workers rush into the space to help. One study has actually found that 20% of fatal hydrogen sulfide incidents involved multiple fatalities. The following video is taken from a construction site and shows a hydrogen sulfide multiple fatalities incidents. Now, before viewing the video, it is important to note here that 3 workers rushed to the scene when they were summoned to rescue 2 other workers who have fallen unconscious due to hydrogen sulfide inhalation. One of the would-be rescuers had not worn the proper breathing apparatus and also collapsed. Despite attempts at resuscitation, the 3 workers died.
Yes.
This tragic accident could have been avoided. The lack of compliance to the site procedure was a key factor in this incident. Now, because of the dangers involved in entering confined spaces, only those employees trained and authorized may enter a confined space. Your company should and must maintain a written confined space entry program that details the safe work practices required to enter each confined space and establishes a written permit entry system to ensure that all hazards have been controlled. Some work areas always have the possibility of a release of hydrogen sulfide above the permissible exposure limit. Perhaps this is the case at your facility. All areas with the potential for hydrogen sulfide should and must have various devices and monitoring systems to detect the presence of the gas. In some cases, fixed point monitors will be installed, as in this example, while in other cases, portable monitors may be used. In either case, these monitors will be calibrated to sound a warning when hydrogen sulfide levels reach the predetermined action levels in your facility's hydrogen sulfide contingency plan. Many facilities utilize a 2-level warning system. For example, one type of warning may be given to alert workers when hydrogen sulfide levels approach the permissible exposure limit. This type of warning may require non-essential workers to leave the area and essential workers to don appropriate respiratory protection. Now, should hydrogen sulfide levels go even higher, such as approaching the IDLH level or other level specified by your organization, an evacuation warning may be given. Always make sure you fully understand what visual or audible signals are used at your facility and their meaning. If an evacuation alarm sounds, you should move upwind swiftly and, if possible, uphill. Avoid low-lying areas, as hydrogen sulfide is heavier than air and thus will collect in these types of areas. If you are not wearing a respirator when an evacuation alarm sounds, hold your breath as long as possible while evacuating. If you have access to a proper respirator, then quickly put it on. Areas with the potential for hydrogen sulfide releases will have a visible wind indicator, such as a wind sock or streamers, to help determine wind direction, as depicted here. These areas should also have more than one escape route to facilitate a safe evacuation. Employees working in hydrogen sulfide-prone areas should remain conscious of wind direction and escape routes. Recall, evacuating employees must report to a designated briefing area so each person can be accounted for. Briefing areas should also be set up at least 250 feet away and upwind from hydrogen sulfide-prone areas. These briefing areas will have prominent signs that can be easily seen by employees. Remember that a high percentage of hydrogen sulfide deaths involve multiple fatalities. During a hydrogen sulfide incident, never attempt to assist a falling worker unless you are wearing appropriate respiratory protection and are trained to assist. In this situation, being a good Samaritan can easily kill you. The same concentration of hydrogen sulfide that quickly overcame your coworker will just as quickly overcome you. Instead, head straight to the briefing area and report the location of your fallen worker. A properly outfitted and trained rescue team can then retrieve the fallen worker and quickly get him to fresh air and medical attention. Lastly, keep in mind, after a release of hydrogen sulfide, do not return to the area until it has been monitored and rendered safe to enter. The following simplified animation illustrates why. This video presents additional safety tips for working in hydrogen sulfide-prone areas. First, never work alone in hydrogen sulfide-prone areas. Use a buddy system. You may actually encounter working areas at your facility where a buddy system is required. In this case, the following safety sign is likely to be displayed. As part of the buddy system, you should always know where your buddy is and be mindful of his or her safety. Keep in mind, hydrogen sulfide is flammable, with a flash point of just 500 degrees Fahrenheit or 260 degrees Celsius. So do not smoke in any hydrogen sulfide area, and do not perform any type of welding or cutting operations without first controlling the hazards and obtaining a hot work permit. In addition, maintain an awareness of wind direction and work upwind of potential hydrogen sulfide sources whenever possible. Some facilities use a color-coded system of warnings so workers approaching a potential hydrogen sulfide area will have knowledge of the current conditions. Perhaps this is the case at your facility. So, if your facility uses such a system, make sure you understand the meaning of each color-coded signal. In this incident involving hydrogen sulfide, a release of this toxic gas led to the death of one worker as well as a member of the public. Here is a brief summary of what happened. Here's how the media covered this tragic accident.
The local couple left behind 2 children. It happened over the weekend during what was supposed to be a routine job at an energy company. Fox 24's Jian Kim has the latest. She joins us now live from the sheriff's office with the details. Jian?
That's right. Such a tragic accident. Husband Jacob Dean was an employee of Acorn Energy. Now, he was called in that night for a maintenance check. Sheriff Griffiths tells me the water coming from a broken equipment inside that pump house was concentrated with H2S gas.
Like I said, it's just an awful, awful situation. 2 little kids have lost their parents, and We need to pray for those folks.
A maintenance check turned deadly for one employee at Acorn Energy.
The gentleman had gotten a call to go out and check this pump. Apparently when he opened the door or something to that effect, he was overcome by H2S gas.
His wife, Natalie Dean, took her 2 kids to check on her husband. Unfortunately, she also inhaled the gas upon walking up to the pump house.
They were both found deceased at that location. She had 2 children in the car with her. They were exposed to some gas, but they were taken to medical center hospital. Appears to be they'll be fine.
Sheriff Griffith says H2S is a byproduct of crude oil and natural gas, a very deadly substance, and just one breath could take their lives.
It's very prevalent in this area. We don't have a whole lot of incidents involving that due to all the training that has gone on throughout the years. I'm not aware if there was a sensor on that location or not.
The 2 bodies will be sent off to Tarrant County for autopsy.
They're part of our community, just like anybody else, and they want the best for our community, and they absolutely do not wish for anything like this to happen.
Now, the investigation remains ongoing at this time, but I'm told that it will soon be turned over to the Railroad Commission as well as the Occupational Safety and Health Administration. Live from Metro County, I'm Gian Kim, Fox 24 News.
October 26, 2019. The Aghorn Operating Incorporated Waterflood Station near Odessa, Texas. One Aghorn employee succumbed to toxic hydrogen sulfide gas that had escaped through a damaged pump. After several hours, when the pumper did not return home, his spouse drove with their 2 children to the station to check on him. She entered the Waterflood Station facility and searched for him. She soon found him on the floor in the pump house. She then was also overcome and fatally injured by the toxic hydrogen sulfide gas. A short time later, emergency responders approached the pump house. They detected a very strong smell of hydrogen sulfide. This required them to set up the command post outside the front gate of the facility and wear self-contained breathing apparatus. They found the pumper and his wife deceased inside the pump house and water spilling from pump number 1. The responders rescued the 2 children who were inside the spouse's car. Working with Aghorn employees, they were able to stop the water release the following morning.
During our investigation, we identified 6 major safety issues at the facility.
One of the 6 safety issues identified was that the pumper was not equipped with his company-issued personal hydrogen sulfide detection device inside the pump house on the night of the incident. When the pumper's personal hydrogen sulfide detector was located in his work truck, it was found to be in an alarm state, meaning it had detected dangerous levels of hydrogen sulfide. The potential for a hydrogen sulfide release was a known hazard at the water flood station, as indicated by the posted signage and a safety pamphlet provided to all employees. However, there was no evidence that Aghorn management required use of personal hydrogen sulfide detectors or adequately trained employees that equipment malfunctions could indicate a toxic hydrogen sulfide release.
Companies should ensure workers always use the required safety equipment, such as personal detectors, when entering a potentially hazardous area. Regular training and posting signs will help remind employees to use their safety equipment every time.
The second safety issue CSB investigators discovered is that at the time of the incident, Aghorn did not have any written lockout-tagout policies or procedures, but relied on verbal procedures without formalized training. On the night of the incident, the pumper did not properly perform lockout-tagout to de-energize the pump before performing work on it. Instead, he started to close the pump's valves while the pump was still configured to be automatically operated by the control system. As a result, the control system automatically turned the pump on, and water containing hydrogen sulfide was able to escape from the pump when the discharge valve was closed.
Companies must have written lockout-tagout policies and procedures that instruct to isolate all possible sources of energy before employees perform work on equipment. Companies also need to routinely train employees on the lockout-tagout procedures.
The third safety issue identified by the CSB was that ventilation inside the pump house was inadequate, leading to fatal concentrations of hydrogen sulfide gas within the building. The CSB found that the pump house could be ventilated by 2 bay doors, exhaust fans, and natural vents on each of the 4 outside walls. Due to the limitations of available evidence, the CSB was unable to confirm whether the exhaust fans were operational at the time of the incident. The 2 bay doors were approximately 60% open, but this was not enough to adequately ventilate the building. And the CSB's investigation could not find any evidence that Aghorn assessed the pump house to ensure it could be properly ventilated, despite the potential for a hydrogen sulfide release to occur inside.
Companies should evaluate any buildings that contain equipment handling toxic gases and determine if the building is necessary. If it is, companies should ensure the building is equipped with a functioning toxic gas detection and alarm system and a ventilation system designed for the release of toxic gases. If the building is not necessary for the operation, a safety assessment should be conducted to determine if removal of the building or relocation of the equipment can prevent confinement of any toxic gas releases.
The fourth safety issue noted by the CSB was the lack of a robust safety management program at Aghorn. Comprehensive safety management practices include risk identification, assessment, mitigation, and monitoring of design, procedures, maintenance, and training. Safety management practices are an essential element of protecting workers and non-employees from toxic gases at chemical plants. At Aghorn, there were no operational, training, testing, and maintenance procedures or records, other than items such as a cell phone use policy and a pamphlet on the hazards of hydrogen sulfide. these items were not sufficient to prepare employees for potential encounters with hazards inherent to their work.
At facilities that handle toxic gases, companies must develop and implement a robust safety management program to protect workers and non-employees from exposure to toxic gas.
The CSB identified a fifth safety issue at Aghorn, which was a non-functioning hydrogen sulfide detection and alarm system. Some of the facility's detectors were set to a testing mode, which prevented them from sending an alarm signal, and other sensors that were correctly set up were unable to send a signal to the control room. As a result, the pumper was not warned of the toxic hydrogen sulfide, either through a telephone alert or illumination of the red pump house beacon light.
At facilities that handle toxic gases, gas detection and alarm systems must be adequately designed, maintained, and tested. Alarms should clearly alert to the hazard through visual and audible indications. Visual indications should be discernible during any time of day. Signs alerting the facility handles toxic gas should be posted in clear view, legible at day and night, and should be well maintained.
And finally, the sixth safety issue, discovered by the CSB at Aghorn, was deficient site security. Per Aghorn's informal policy, when an Aghorn employee is working at the facility, the access gates are normally left unlocked. On the night of the incident, this practice allowed the pumper's spouse to drive directly to the water flood station and enter the pump house, where she was also fatally injured.
Effective site security must be in place to prevent non-employees from accessing hazardous areas.
In a chemical facility, a vessel with wastewater containing 5 ppm weight of hydrogen sulfide at 30 degrees Celsius is located below grade. A maintenance team issued a general work permit to inspect the pipe connected to the vessel. The plan was to access the equipment using a ladder. Process safety engineers inquired about the necessity of installing some gas detectors in the confined space and possibly to classify the zone as a restricted area. The very low hydrogen sulfide concentration, 5 ppm in the water, convinced them not to take into consideration the detection system. The work permit was approved and the maintenance team proceeded. One operator entered the pit unprotected and collapsed due to hydrogen sulfide inhalation while working on the vessel. Another operator in the vicinity immediately entered the pit to attempt a rescue, but he also collapsed. Despite attempts at resuscitation, the 2 men died. So what went wrong? What really happened inside this confined space? How could 5 ppm of hydrogen sulfide kill 2 men? Isn't the hydrogen sulfide IDLH at 100 ppm? Well, in this particular case, the assumption initially made by the process safety engineers was clearly wrong. Although the concentration of dissolved hydrogen sulfide in the water was only 5 ppm, the concentration of hydrogen sulfide over the water surface was way greater than this. It was actually even above the IDLH level that it killed 2 operators immediately, as depicted here. Now, although the explanation that will follow will be broken down into further details in the process safety calculation section of the course, here is a brief description. The following figure illustrates gas-liquid concentration of hydrogen sulfide in water. The inclined solid lines, starting from 0.5 all the way to 6, represent the concentration of dissolved hydrogen sulfide in water, expressed in milligram per liter or ppm and as a function of temperature. The y-axis that you can see here represents the corresponding hydrogen sulfide concentration in air, or in other words, the corresponding hydrogen sulfide concentration above the water surface. In our example, at 30 degrees Celsius, for 5 ppm of dissolved hydrogen sulfide in water, the concentration of hydrogen sulfide in air above the water level would be 1650 ppm. This is way above the IDLH of 100 ppm. What it means is that under these conditions, the air around the vessel is not fit to breathe. Hydrogen sulfide has reached dangerous levels, turning the space into a toxic, deadly atmosphere. A simple risk assessment would have helped those responsible to identify at least 3 major safety issues at the facility. The first safety issue is that the maintenance workers were not equipped with personal hydrogen sulfide detection device when entering the confined space, and were not wearing respiratory protection. Although the potential for hydrogen sulfide release was a known hazard at the facility, process safety engineers overlooked the exposure to hydrogen sulfide in this particular case, and were unable to appreciate the overhead deadly concentration levels. The second safety issue is that ventilation of the confined space was inadequate, leading to fatal concentrations of hydrogen sulfide gas. the confined space could have been ventilated by exhaust fans. The third safety issue is the absence of a hydrogen sulfide detection and alarm system. As a result, the workers were not warned of the toxic hydrogen sulfide. Keep in mind and always remember, at facilities that handle toxic gases such as hydrogen sulfide, gas detection and alarm systems must be adequately designed, maintained, and tested. Alarms should clearly alert to the hazards through visual and audible indications. Visual indications should be discernible during any time of day. In addition, signs alerting that the facility handles toxic gases should be posted in clear view, legible at day and night, and should be well maintained. If your facility handles such substances, please make sure you comply with these safety measures. Thank you again for taking our online course. We hope that the short section on hydrogen sulfide has made it clear for you that contact with this toxic gas can prove fatal in a matter of seconds. Please feel free to share what you have learned from this course with others, since this is one of the most effective means of communicating lessons learned and avoiding incidents in the future. Thank you for watching. This section provides a brief description of nitrogen hazards. 2 accidents involving nitrogen will be presented to raise your safety awareness. Then, because nitrogen is handled routinely in chemical plants, we have dedicated a separate section to this hazardous but essential material. The following table summarizes the most important properties and characteristics of nitrogen relevant to safety. It is important to note here that nitrogen, when misused, has a potential almost equal to that of hydrogen sulfide in producing fatal gassing incidents. Nitrogen is considered a hazardous material not because it is poisonous like hydrogen sulfide, but because the gas displaces oxygen in the atmosphere, causing asphyxiation in humans. Unless oxygen is supplied quickly to the victim, death quickly follows. There have been instances where nitrogen was used in place of breathable air, which have resulted in fatalities. Now, what I want you to keep in mind at this stage is the following. Nitrogen is an asphyxiant gas. Continued exposures lead to faulty judgment, depression of senses, rapid fatigue, unconsciousness, convulsions, coma, and even death. During a nitrogen incident, never attempt to assist a falling worker unless you are wearing adequate respiratory protection and are trained to assist. In this situation, being a good Samaritan can easily kill you. The same concentration of nitrogen that quickly overcame your coworker will just as quickly overcome you. Instead, head straight to the briefing area and report the location of your fallen worker. A rescue team can then retrieve the victim and quickly get him fresh air and medical attention. Also, please remember, nitrogen is a simple asphyxiant. Do not use cartridge-type respirators. These are ineffective. Instead, use a powered supplied air respirator or a positive pressure SCBA with full face piece, as depicted here. In this tragic accident, an operator removed the cover from this manhole completely to take a sample of the atmosphere from the reactor. The reactor was under nitrogen purge at the time. As a result, he became asphyxiated and fell to his death through the open manhole. The operator was working alone and had not been warned of the oxygen-deficient atmosphere and the necessity to wear breathing apparatus prior to sampling. It is important to recognize here that there was inadequate assessment of the needs and risks associated with taking samples from the nitrogen-rich atmosphere. So please keep this in mind. When breaking containment, follow all safety procedures associated with the system and type of material expected, and the use of appropriate respiratory protection. Sampling, although seems an easy, simple task, is a hazardous activity, not only because the sampler may be exposed to oxygen-deficient atmosphere or even toxic atmosphere, but also because the activity can generate sparks through static electricity and ignite flammable materials within the equipment, vessel, or tank. In this example, nitrogen was used in place of breathable air and resulted in a fatality. Following a power failure at the plant, instrument air was switched over to nitrogen backup. Later on, an instrumentation technician entered the analyzer house, only to be discovered unconscious on the floor sometime later. He was removed from the analyzer house, but a site first aider was not able to resuscitate him. He was taken to the local hospital and later pronounced dead. In this accident, the controls and safeguards that were required to be completed prior to switching over from instrument air to nitrogen gas had not been fully implemented, one of which should have been the locking of the analyzer house doors. The design of the analyzer house permitted a nitrogen-rich atmosphere to develop by using instrument air as a purge. As a result of this administrative breakdown, the instrumentation technician was asphyxiated when he was allowed to enter the analyzer house. For this reason, any equipment, tank, vessel, analyzer house containing nitrogen and with the potential to develop a nitrogen-rich atmosphere should be clearly identified. A warning sign, as in this example, should have been attached to the door of the analyzer house. In this video, we will talk about an extremely hazardous chemical routinely used in oil refineries and many chemical facilities. This hazardous material is hydrogen fluoride. As seen here, this substance is toxic, corrosive, fatal if swallowed, inhaled, or in contact with skin, and is usually handled, processed, stored, and manipulated under pressure. A very nasty stuff. For this reason, any exposure to hydrogen fluoride should be considered a medical emergency. Let me say this once again. Any exposure to hydrogen fluoride should be considered a medical emergency. Now, to begin our discussion, the following table summarizes the key properties and characteristics of hydrogen fluoride. Needless to say that the data found in this session should not be used as a replacement for your site safety data sheets. Hydrogen fluoride, or simply HF, is a colorless, corrosive gas above 20 degrees Celsius or 69 degrees Fahrenheit, and a clear, colorless, corrosive, fuming liquid at lower temperatures with an extremely irritating odor. It readily dissolves in water to form HF acid, which is also a colorless liquid that fumes in higher concentrations. Keep in mind though, in all forms, hydrogen fluoride can be extremely destructive to human tissues and a wide range of other substances, including most metals, concrete, and glass. HF can be absorbed into the body through ingestion, inhalation, and eye or skin contact. It can easily penetrate the skin and cause cellular damage and systemic toxicity. The severity and timing of symptoms are dependent on the concentration and duration of exposure. Keep in mind for your own safety, exposure to HF can be fatal, and again, any exposure should be considered a medical emergency. In general, exposure to a low concentration of hydrogen fluoride vapor for a short time, either in anhydrous form or from water solutions, can cause skin and eye irritation. Severe damage to skin, eyes, other tissues, respiratory system, and death can occur with exposure to higher concentrations. Burns from HF are particularly dangerous and require immediate and special treatment by trained medical personnel. As a safety best practice, working with HF should only be permitted when a fluoride binding agent is on hand. Typical examples of fluoride binding agents are now shown on screen. If your facility handles, stores, processes, or transports HF, please make sure you have such systems at your disposal. Swallowing only a small amount of highly concentrated HF will affect major internal organs and may be fatal. Breathing HF gas may cause eye, nose, and respiratory tract irritation immediately, or up to 36 hours later, even at low levels. Breathing in hydrogen fluoride at high levels or in combination with skin contact can cause death from irregular heartbeat or from fluid buildup in the lungs. The following table summarizes the signs and symptoms upon contact with skin and depending on level of concentration. As seen here, skin redness, severe burning, and pain may not appear for several hours following exposure to a 20% solution of HF. Burns are apparent within 1 to 8 hours after exposure to 20 to 50% HF solutions. Immediate pain and tissue destruction occur following exposure to a 50% solution of HF. Even small splashes of high concentration HF on the skin can cause death. So, for your own safety, remember, any exposure to HF should be considered a medical emergency. Lastly, direct HF splashes to the eye are extremely damaging. exposure to concentrated HF vapor may result in adverse effects several hours following exposure. Dilute solutions may produce delayed adverse effects as long as 4 days after the exposure. So again, keep in mind, any exposure to HF should be considered a medical emergency. People who survive after being severely injured by breathing in HF may suffer chronic lung disease. Skin damage caused by concentrated HF may take a long time to heal and could result in severe scarring. Fingertip injuries may result in persistent pain, bone loss, and injury to the nail bed. Eye exposure may cause prolonged or permanent visual defects, blindness, or destruction of the eye. Swallowing HF can damage the stomach and other organs. Now, the best way to prevent exposure is to substitute with a less toxic chemical. Recall, what you don't have can't leak and can't pose threat to life. This is part of the inherently safer design philosophy. However, if working with HF is the only option, then implement engineering and administrative controls. Where such controls are not feasible or do not adequately reduce HF exposures, then conduct a hazard assessment and select suitable PPE accordingly. The following are some best practices. Pump from closed HF containers whenever feasible. Wear a long-sleeved shirt, long pants, and closed shoes even when working with small quantities of dilute forms of HF. Add PPE based on the risk of worker exposure, quantities, and the concentration of HF being used. Always protect the eyes and face with goggles and a face shield whenever there is a risk of exposure. And, where feasible, work in a chemical fume hood or use other forms of ventilation that control HF vapor emissions at the source. Besides PPE, consider using a barrier to reduce risk of exposure to splashes. Wear an HF-resistant full-body apron and chemical-resistant boots anytime there is a risk of splash. Ensure there is no splash intrusion between the boot tops and legs. Use appropriate HF-resistant gloves and select chemical boots, aprons, and gloves based on potential exposures to HF and the nature of the work, taking into consideration concentration and contact time. Also, consult the safety data sheet and manufacturer of the PPE being considered to help determine adequate material, breakthrough protection, and permeation times. Lastly, wash hands and arms at the end of procedures involving HF has been removed. The figures that will follow show the correct way to remove used gloves to avoid contamination. As seen here, first grasp the outside of one glove, then hold the glove with your gloved hand. Next, insert your fingers on the inside of the glove, and lastly, turn the glove inside out over the first glove. Of course, this procedure is valid for all kinds of hazardous substances, not only HF. In addition, don't forget to make sure that the safety data sheets for the HF being used at your facility is readily available. Also, ensure containers, vessels, or tanks are properly labeled and consider posting warning signs in the work area, as depicted here. This will raise the awareness of workers so that they can recognize early signs of safety concerns and spot early signs of equipment damage or deterioration. Now, in case of loss of containment, spill, HF release into the atmosphere, rescuers should wear full protective clothing and be equipped with a self-contained breathing apparatus, similar to that discussed for hydrogen sulfide. And in case of fire around HF equipment, vessels, containers, or tanks, water can be sprayed to keep fire-exposed equipment and containers cool. But keep in mind, HF in the presence of water can produce explosive hydrogen gas. So, rescuers should also be equipped with combustible gas detectors. Worker skin and airborne exposures to HF must be evaluated by a qualified individual. A physician who is board certified in occupational medicine should provide consultation to develop an appropriate medical program for management of exposures and monitoring of employees working with HF. If your facility handles, stores, processes, or transports HF, please make sure that a medical program for management of exposures of employees is in place. Okay, now before starting work, consult your safety data sheet for the specific concentration and form of HF being used at your facility and confirm with your medical service provider what procedures should be implemented. For example, in case of skin exposures, which fluoride binding agent should be used for first aid. Now, in most cases, using calcium gluconate will be the most practical solution. But again, this has to be confirmed with your medical service provider. Also, before starting work, confirm the location and adequate stock levels of fluoride binding agents and spill cleanup materials, and ensure that emergency eye washes and showers are functioning properly and also are immediately accessible to exposed workers. Needless to say that all workers involved in hydrogen fluoride processing, handling, manipulating, or storing should be adequately trained, not only on how to do all these operations safely, but also in terms of first aid and how to respond to emergency situations. Now, what to do in case of exposure? When exposure to HF occurs or is suspected, you should implement the procedures provided in the safety data sheet or those recommended by your medical service provider. Do not wait for symptoms to appear. Seek urgent care from your medical service provider or, if necessary, a hospital. When an exposed worker is taken to a hospital, it is important to ensure that the safety data sheet of the HF in question goes with him. The medical staff should be aware of the type of exposure and the chemical involved. This is extremely important, not only to protect the medical staff and potentially hospital patients, but also to guarantee that adequate care will be provided to the exposed worker. In case of skin exposure, immediately and carefully remove contaminated clothing and jewelry in order to avoid additional contact. Flush exposed skin with water for at least 15 minutes before applying a fluoride binding agent. If a fluoride binding agent is not available, flush exposed skin with water for at least another 30 minutes. Double glove to apply a fluoride binding agent as soon as possible after washing and while the exposed worker is being taken to the hospital. The fluoride binding agent should be reapplied frequently and massaged into the affected area. In case of eye exposure, immediately rinse eyes using an emergency eye wash for at least 30 minutes. Don't forget to remove and discard any contact lenses. Lift eyelids and move eyes to ensure complete irrigation. After that, the exposed worker should be urgently transported to medical care. Now, if hydrogen fluoride is released into the air, evacuate the area or shelter in place as directed by your supervision and according to your workplace emergency action plan. Also remember, emergency transport to a hospital is required even when symptoms are not initially obvious. In case of inhalation or ingestion, the exposed worker should be transported immediately to medical care. In these instances, do not induce vomiting. This can make the situation even worse. Contaminated clothing and jewelry should be placed inside a polyethylene bag. When doing so, avoid touching contaminated areas of the clothing. If that is not feasible or extent of contamination is not known, use sticks or similar objects to place clothing in a bag. Keep in mind, anything that touches contaminated clothing should also be placed in the bag. Next, seal the bag and then seal that bag inside another polyethylene bag and separate it from other types of waste. Do not mix with solvents, organic acids, oxidizers, or other chemical waste. Ensure that anyone else that may handle the bag is aware of the hazard, so that they can protect themselves as well. Lastly, when local or state health department or emergency response team arrive, tell them what you did with the clothing. Anhydrous ammonia is a common chemical used in manufacturing, the treatment of metals, and chemical processing. It is also an essential element of fertilizer and is used in a wide variety of industries as a refrigerant and as part of the air scrubbing process to reduce carbon emissions. As beneficial as anhydrous ammonia is to these processes, it can also be very dangerous. Workers who become exposed to anhydrous ammonia can suffer serious injuries, health effects, or even death. To prevent harmful exposures to this useful chemical, the Occupational Safety and Health Administration has developed safety standards that regulate the use of anhydrous ammonia in the workplace. This section discusses some key requirements from these regulations, as well as safe work practices and procedures which are necessary to prevent harmful exposures to anhydrous ammonia. After completing this section, you should be able to explain the following: the characteristics and properties of anhydrous ammonia, the effects of an exposure, the OSHA regulations involved in working with anhydrous ammonia, the PPE and safe work practice controls for handling anhydrous ammonia, and how to respond to an exposure. Anhydrous ammonia is a compound that is made of 1 part nitrogen and 3 parts hydrogen. Anhydrous ammonia is often referred to by its molecular formula, NH3. The word anhydrous means without water, which distinguishes this type of ammonia from the aqueous forms of ammonia, which are commonly used as cleaners and disinfectants. The fact that anhydrous ammonia contains no water contributes to its hazardous nature. When anhydrous ammonia contacts any type of moisture, it quickly combines with water to form ammonium hydroxide, as depicted here. Ammonium hydroxide is a very caustic solution, which can cause irritation and burns to human tissues. At room temperature, anhydrous ammonia is a colorless gas with a pungent odor. In fact, the odor is so strong that you cannot voluntarily stay in an area of high concentration for very long, because you literally won't be able to stand the smell. The boiling point of anhydrous ammonia is negative 28 degrees Fahrenheit. Because it has such a low boiling point, large volumes of anhydrous ammonia must be shipped and stored as a liquid. To be stored in its liquid state, anhydrous ammonia must be kept under very high pressure or be maintained below its boiling point of negative 28 degrees Fahrenheit. If liquid anhydrous ammonia is allowed to escape into room temperature and pressure, it will rapidly transform into a gas, forcibly expanding in volume and instantly cooling to negative 28 degrees Fahrenheit. These extreme cold temperatures can cause severe frostbite and tissue damage. In addition, the rapid expansion and cooling of escaping anhydrous ammonia can cause severe injuries or death, and the caustic nature of ammonium hydroxide can cause burns and other health effects. This is why workers must always take proper precautions to avoid creating an anhydrous ammonia leak or other harmful exposure. At normal temperature and pressure, anhydrous ammonia is a gas that is both corrosive and toxic. When anhydrous ammonia comes into contact with your eyes, skin, lungs, or any mucous membrane, it will combine with the moisture present in these tissues, causing tissue dehydration, cell destruction, irritation, and chemical burns. In addition, many injuries also occur from unexpected high-pressure releases of anhydrous ammonia. The force of the expanding gas can cause severe injuries, while the extreme cold temperature of anhydrous ammonia can also cause severe frostbite and tissue damage. Anhydrous ammonia is also a respiratory hazard and can be fatal when inhaled at high enough concentrations. When concentrations of anhydrous ammonia exceed 300 ppm, it presents an immediate danger to life and health. Recall, this potentially fatal level of concentration is also referred to as the IDLH level. Some symptoms of respiratory exposure include irregular breathing, shortness of breath, choking, or respiratory arrest. In order to protect workers from injury and illness related to anhydrous ammonia, the Occupational Safety and Health Administration has issued a standard titled Storage and Handling of Anhydrous Ammonia. In addition, OSHA has also published limits for employee exposure to anhydrous ammonia in Table Z1 titled Limits for Air Contaminants. OSHA has set the permissible exposure limit, or PEL, for anhydrous ammonia at 50 parts per million over an 8-hour time-weight average. When levels of anhydrous ammonia exceed this permissible exposure limit, organizations must take measures to reduce the amount of anhydrous ammonia in the air. If the levels of anhydrous ammonia cannot be reduced by other means, then workers must be provided with the appropriate respiratory protection and other PPE necessary to avoid harmful exposure. In addition to OSHA, there are other organizations that issue exposure guidelines. Two such organizations are the National Institute for Occupational Safety and Health and the American Conference of Governmental Industrial Hygienists. The first one publishes a recommended exposure limit, or REL, of 25 parts per million averaged over a 10-hour period, while the second one published a threshold limit value, or TLV, of 25 parts per million averaged over an 8-hour period. These organizations also recommend a short-term exposure limit, or STEL, of 35 parts per million for a 15-minute period of exposure. Now, it is important to note here that the recommendations of these two organizations are not legally binding and often exceed OSHA's requirements. When exposure levels cannot be reduced to permissible levels, or there is the potential for an accidental release of anhydrous ammonia, workers will be required to wear appropriate respiratory protection. However, before using any type of respirator or breathing apparatus, you must undergo a medical evaluation by a licensed physician who will determine your physical ability to use the equipment effectively. You will also be trained in the selection, care, and proper use of your respirator, as well as the techniques you must use to achieve a proper fit and how to verify that the respirator is properly sealed to your face. When working in conditions where there is the potential for exposure up to 250 ppm, a half-face respirator, as seen here with chemical cartridges that provide protection from ammonia, may be used. Now, for concentrations up to 300 ppm, a full-face respirator with chemical cartridges may be used. When using these types of cartridge respirators, you should not be able to smell any ammonia. If, however, you do smell ammonia, then your cartridges may need to be changed, or you may not have a proper seal. Now, if ammonia concentrations may be above the IDLH level of 300 ppm, or the potential level of ammonia concentration is unknown, then a self-contained breathing apparatus operating in positive pressure mode must be used. If you are unsure how to use your respirator or have questions about cartridge selection or proper fit, stop and ask for help. Never rush to a scene without proper respiratory protection. Keep in mind, exposure to anhydrous ammonia can also be damaging to the skin and eyes. This is why various types of personal protective equipment will be required when working with or near anhydrous ammonia. To avoid general skin exposure, long-sleeve chemical-resistant protective clothing, as seen here, offers good protection. Of course, the level of protection chosen should match the potential level of exposure. To protect the hands, loose-fitted neoprene butyl rubber gloves with extended cuffs should be worn. The cuffs should be turned up so ammonia will not run down your arms when they are raised. In addition, gloves that fit loosely can be removed more easily in case of an emergency. If you happen to work with ammonia that is used as a refrigerant, you may want to wear lined gloves to keep your hands warm when handling cold metal pipe. To protect your eyes, non-vented safety goggles, as seen here, should be worn. For additional protection of the face, a face shield can be worn in combination with safety goggles. Keep in mind, a face shield alone does not offer any protection for your eyes, so always wear eye protection in combination with a face shield. To finish off this video, please keep in mind the level of required PPE will depend on the potential concentrations of an exposure. Always wear the personal protective equipment required by your company when working with or near anhydrous ammonia. The potential for unexpected releases of anhydrous ammonia is greatest when it is being transported or transferred. In addition, the failure of hoses, valves, storage vessels, or pressurized piping systems can be the cause of a major release of anhydrous ammonia. When working with tanks and transfer equipment, they must be inspected frequently. Transfer hoses and relief valves are the two most important elements of an inspection process. Relief valves have a replacement date stamped on the valve body, so make sure this date has not passed. All hoses should be free of cuts, worn spots, or other damage. Hoses must be labeled anhydrous ammonia and be marked with the year of manufacture and an expiration date. Hoses whose expiration date has passed must be removed from the service immediately. Make sure that all connections are clean and free of dirt and debris. Threaded connections must be in good conditions. Be aware that all storage, handling, transfer, and other equipment must be approved for use with anhydrous ammonia. Unapproved equipment must be incompatible with anhydrous ammonia or may fail under the high pressures involved. Tanks used to store anhydrous ammonia should be painted silver or white to best reflect heat. Tanks should never be filled greater than 85% capacity to allow for the expansion of the gas as the temperature or pressure changes. And before operating any valve that controls anhydrous ammonia, all workers involved in the process must read and understand the valve operator's manual. This valve operation training must be documented. In addition, tanks containing anhydrous ammonia must be secured in place before any valve may be operated. This helps ensure that active connections are not inadvertently broken due to any shifting or movement of the tank. Anhydrous ammonia tanks must also be located where there are no obstructions to escape from the area if a leak develops. During the transfer process, employees should stay a distance away and upwind of the involved valves and hoses. If a release does occur, immediately evacuate the area to a safe location while also alerting others to the danger. Follow your company's emergency response plan for reporting the situation. And remember, never attempt to control or contain ammonia leaks unless you have been properly trained and authorized, as well as having the necessary protective equipment such as a self-contained breathing apparatus and protective chemical-resistant suit. Finally, keep this in mind for the safety of your fellow workers and yourself. No one should be allowed to return to the area until the situation is remedied and the all-clear command is issued. Despite all of our efforts, there is always the risk of exposure when handling or working near anhydrous ammonia. Properly responding when someone is sprayed with liquid ammonia or engulfed in a cloud of vapors can significantly limit the seriousness of any resulting injury. If a person's eyes or skin have been exposed, get him or her to an eye wash station, safety shower, or sink immediately. Flush the affected area for 15 minutes. Use as much water as possible, as it will dilute the ammonia and reduce its potential to damage the skin. Do not attempt to remove any clothing at this point. In many cases, the extreme cold temperature of anhydrous ammonia will freeze exposed clothing to the skin, and removing it can cause additional injury to the skin. Wait until contaminated clothing has been thawed before removing it. If ammonia has entered the eyes, make sure to hold the eyelids open while flushing with large amount of water for 15 to 20 minutes. Now, of course, needless to say that you must know where the safety shower and eye wash stations are located in your workplace. You must be able to find and operate them even with your eyes closed. If someone has inhaled low levels of ammonia, move the victim to a safe area with plenty of fresh air and monitor their condition. Higher concentration exposures may result in convulsive coughing or respiratory spasms and require immediate medical assistance. Having said that, keep in mind all exposures to anhydrous ammonia, even those that seem minor, require medical attention and evaluation. So always report any exposure right away. An operator inhaled ammonia vapors during maintenance work on a small diameter valve connected to an ammonia tank. Believing that the work environment was safe, he had removed his breathing equipment, presumably to see more clearly. He was then taken to hospital, kept in overnight, and discharged. He was readmitted the following day with a throat infection which had developed. The main safety message here is as follows. All known hazards must be removed or adequately controlled and communicated before work permits are issued. an operator connected plant air to an aqueous ammonia tank in an effort to speed up unloading instead of using a small air compressor. The tank was overpressured and split open, flooding the area with liquid ammonia, as seen here. The refinery firefighting crew was quick to dilute the ammonia with water. Now, the use of water sprays in tackling aqueous solutions of ammonia was correct here, but keep in mind extra care must be taken in the application of water to anhydrous ammonia. The heat of reaction between water and anhydrous ammonia can lead to a more rapid vaporization of the ammonia. In addition, recall, when anhydrous ammonia contacts water or any type of moisture, it quickly combines with water to form ammonium hydroxide, which is a very caustic solution that can cause irritation and burns to human tissues.
The Millard facility experienced a loss of power that lasted more than 7 hours. During that time, the refrigeration system was shut down. The next day, the system regained power and was up and running, though operators reported certain problems. While doing some troubleshooting, an operator cleared alarms in the control system, which reset the refrigeration cycle on a group of freezer evaporators that were in the process of defrosting. The control system reset triggered a valve to open, and low-temperature liquid ammonia was fed back into the evaporator coils before removing the hot ammonia gas. This caused the hot, high-pressure ammonia gas to rapidly condense into a liquid. A vacuum was created, where the gas had condensed. The void sent a wave of liquid ammonia through the piping, causing a sudden pressure surge known as hydraulic shock. The pressure surge ruptured the evaporator piping manifold inside one of the freezers, and its associated 12-inch piping on the roof of the facility. 32,100 pounds of ammonia were released into the surrounding environment. The large cloud traveled a quarter mile from the facility, south toward an area where 800 contractors were working outside on a cleanup site for the Deepwater Horizon oil spill. 153 people were exposed to toxic anhydrous ammonia. 32 of the off-site workers required hospitalization. 4 of them were admitted to an intensive care unit.
The accident example that will follow depicts an ammonia explosion that occurred in a fertilizer plant. The purpose of this video is to remind you that anhydrous ammonia is not only toxic, but also flammable. It is true that we are primarily concerned with the toxic property of anhydrous ammonia, but don't forget that anhydrous ammonia is also flammable and can ignite violently. On the day of the accident, a fire started in the fertilizer building. The fire then spread to the anhydrous ammonia tank, where anhydrous ammonia is stored under pressure to keep it in a liquid state. The fire provided direct flame impingement on the tank surface and caused the tank to fail, leaking flammable ammonia gas. 12 emergency responders and 3 members of the public died as a result of the explosion. The plant was completely destroyed. More than 150 nearby homes and businesses were damaged, some beyond repair. Chlorine is a greenish-yellow toxic gas with a strong irritating odor similar to that of bleach. The following picture depicts a chlorine gas release. Now, if the temperature of the gas is lowered or it is pressurized, it becomes a liquid. In most cases, chlorine gas is shipped as a liquid. Because chlorine is very reactive, it does not exist as a gas in nature. However, it is often found combined with other elements. The most common chlorine compound is salt, or sodium chloride, which is found naturally in seawater and rock salts. The odor threshold of chlorine is about 0.4 ppm. However, remember, odor is not a reliable indicator. Operators exposed routinely to chlorine may lose the ability to smell the chemical at lower levels. Chlorine gas is 2.5 times heavier than air and will tend to collect in low-lying areas where the concentration is high enough. The following video illustrates this. Following this vertical up release, the chlorine cloud begins drifting downwind, levels off horizontally, and begins to arc back down to the ground. Chlorine releases that are vertically downward or at a downward angle will not rise too far, and in a similar manner will hug the ground and settle in low-lying areas. It is important to note here that wind and weather will cause a chlorine gas cloud to disperse, spreading it in all directions, and in some situations even uphill. This will be discussed in further detail in the process safety calculation section. Now, as mentioned, liquid chlorine is maintained in that state in pressurized containers. Liquid chlorine is a transparent, amber-colored substance that is heavier than water. It changes from a liquid to a gas immediately when released from a compressed gas cylinder. Liquid chlorine vaporizes quickly and does not remain as a liquid under ambient conditions. Chlorine has a high compression ratio. The ratio of chlorine liquid to gas is 1 to 460. What this means is that 1 liter of liquid chlorine will expand to 460 liters of pure chlorine gas. In other words, if all the liquid chlorine were to escape from this 65 kilogram container, enough pure chlorine gas will be released that 24 times the amount of air contained in this stadium would be required to dilute it to a safe level. This translates to a gas concentration of 0.5 ppm, which is the TLV, the maximum allowable concentration a person can be exposed to, average over an 8-hour period. Now, although chlorine is not flammable, it is a strong oxidizer. If chlorine comes in contact with flammable or combustible materials such as gasoline, alcohols, hydrogen, ammonia, or sulfur, a fire or explosion can result. The most common way for chlorine to come in contact with incompatible substances is through spills and releases. The video that will follow illustrates what happens when chlorine gas comes in contact with oil. Hazardous conditions can also result if chlorine comes in contact with any of these substances. Chlorine reacts readily with many organic chemicals, and often violently. Some materials will burn in a chlorine atmosphere even if there is no oxygen. Chlorine is also incompatible with moisture, water, and steam, forming corrosive acids when mixed. At 250 degrees Celsius, chlorine will oxidize steel, essentially burning it. In the next demonstration video, you can see what happens when a steel wool is dropped into chlorine gas. Chlorine also reacts with steel at lower temperatures under certain conditions. Oxidation will lead to a fire, which should be avoided since water cannot be used on a chlorine fire. Now, recall, chlorine exists as a gas or a liquid. This chart compares the properties of chlorine gas and liquid. Again, it is important to remember that gaseous chlorine is heavier than air, so it will settle into low areas, such as basements, creek beds, and ravines. Liquid chlorine becomes a gas at negative 29 degrees Fahrenheit at atmospheric pressure. Liquid chlorine has a clear amber color, while chlorine gas will exhibit a faint yellowish color at low concentration and greenish yellow to green at higher concentrations. Depending on the humidity, chlorine gas is usually not visible at concentrations below about 25 ppm. Now, for comparison, we'll view a side-by-side of a heavier-than-air material, chlorine, and a lighter-than-air material, anhydrous ammonia. Very quickly, the chlorine sinks to the ground, while the ammonia fills the airspace as the volume of ammonia increases, even blocking the view of the tank. Even though both of these materials are considered toxic inhalation hazards, you can tell by this video that there are different strategies to respond to an emergency involving chlorine versus a lighter-than-air material. The way ammonia rises is a significant consideration for any elevated surface and any personnel protection plan. In contrast, chlorine runs along the ground or seeks lower elevations. The chlorine reaches the end of the ditched area and basically stagnates. The ammonia, on the other side, has engulfed the entire viewing area of the camera, and the tank is almost no longer visible. Chlorine is one of the most commonly manufactured chemicals in Europe and in North America. Chlorine is used to make chlorinated organic chemicals such as vinyl chloride monomer, carbon tetrachloride, and chlorobenzenes. Also to make organic chemicals such as propylene oxide and glycols, and chlorinated inorganic chemicals such as sodium hypochlorite, hypochlorous acid, sulfur chlorides, and so on. Chlorine is also widely used in the following applications. Chlorine gas is a severe irritant to the eyes and respiratory system because it reacts with body moisture to form acids. Chlorine gas or liquid can also burn the skin. People who are exposed to chlorine can develop some tolerance to its odor and irritating properties. Most of the inorganic chlorine compounds have similar health effects to chlorine, but in varying degrees of severity. Operators are exposed most often to chlorine from inhalation or skin contact with the gas or liquid. Direct contact with liquid chlorine and the skin can cause frostbite as well as severe burns, as depicted here. Poisonous gases can be released when chlorine compounds are mixed with other chemicals. For example, mixing chlorine compounds with acids will release chlorine gas. The following table summarizes the short-term health effects from exposure to chlorine. It is important to note here that the IDLH for chlorine is only 10 ppm. For concentrations between 10 and 25 ppm, chlorine may be fatal after 30 minutes of exposure. And for concentration above 1000 ppm, chlorine is fatal after a few breaths. This emphasizes the extreme toxicity of this hazardous substance. Lastly, keep in mind, workers who have pre-existing lung disorders, for example asthma or allergies, tend to be more sensitive to the irritating effects of chlorine. Chronic exposure to low levels of chlorine gas can cause dermatitis, tooth enamel corrosion, coughing, chest pain, and sore throat. Workers who have had one or more exposures to chlorine that caused acute health effects may have long-term damage to the lungs. The use of personal protective equipment or PPE is critical to the safety of the responder and to the success of the containment of the chlorine release. It is also important to remember that the level of PPE is dependent upon the incident and should be appropriate to the necessary response. Using a level of PPE that is not sufficient for a proper response will endanger the responder. Using a level of PPE that can be considered overkill to the incident could actually hinder the containment. The information covered in this video is not intended to illustrate proper PPE in detail, but to provide additional information relative to the chlorine response. Now, if you happen to work at a chemical facility that handles, stores, manufactures, or uses chlorine, then your facility's emergency response plan describes in detail the recommended levels of protection for emergency responses to chlorine incidents. However, keep in mind certain criteria must be met before implementing these recommendations. These criteria are the following. First, the substance of the release has been identified. No other chemicals other than chlorine are involved in the release. Knowledge of the emergency response planning guidelines for chlorine is essential. Employees are trained and experienced in the use of PPE. A detailed plan for site safety has been developed, and an incident commander is in place and in charge. Now, there are several levels of PPE, and its proper use is a complex topic. This video will cover the PPE that is recommended for a chlorine response. Initial entry should normally be done in Level A protection. By Level A protection, we mean air supply respirator with full face piece and auxiliary self-contained air supply, including escape air provision. Consideration can be given to lower the protection level of PPE after the situation has been assessed. Air monitoring also plays a critical role in a chlorine response. Accurate monitoring will help determine the level of PPE that is appropriate for the response. It helps determine safe areas and evacuation zones. And air monitoring helps control response tactics, as in deciding if or when to move the command post to another safe area due to changing conditions. Uses of detection equipment include the determination whether a hazard is present, the determination of the level of a known hazard, identifying unknown hazards, assessment of health and safety effects, and documents the response timeline. Level B protection should be used when a high level of respiratory protection is required, but skin protection is less critical. Level B provides a high degree of respiratory protection by incorporating a self-sealing suit or chemical-compatible tape on the openings for feet and hands. However, Level B protection is not recommended for confined spaces. Enhanced Level B protection should be used when a high degree of both respiratory and skin protection is necessary. Enhanced Level B protection is appropriate for exposure to several types of chemicals. It is defined as follows: positive pressure full face self-contained breathing apparatus SCBA, or air supply respirator ASR with an auxiliary self-contained air supply, in addition to protective clothing including chemical protective suit, footwear or footwear cover, hood for protection of head and neck, and undergarments to provide thermal protection for exposure to liquid chlorine. Enhanced Level B protection provides fully encapsulated protection, but keep in mind it is not gas-tight. The self-contained breathing apparatus, or SCBA, is an important component to effective PPE. There are, however, advantages and disadvantages to using SCBA. It provides the highest available level of protection against airborne contaminants, but SCBA is also heavy and bulky. It has a finite air supply which limits work duration and may impair movement in confined spaces. For this reason, air monitoring plays a critical role in the chlorine response. Continued environmental monitoring for the duration of the response provides valuable information which will allow the responders to reduce the level of protective equipment they utilize during the response, and also assists in determining when individuals that might have been displaced by the incident can return. Chlorine will be present in transportation containers and at chlorine production, storage, repack, and consumer facilities. Due to the properties of chlorine, most likely the only form of chlorine that a responder will encounter during a release is a gas. Exposure to liquid chlorine will be unlikely unless it occurs at the exact release point. The most common types of chlorine releases are from minor valve leaks that are easily mitigated and have minimal dispersion and ecological effects. For more significant releases, there are three types of releases: instantaneous, continuous, and intermittent. An instantaneous release is characterized by the release of chlorine into the atmosphere in a relatively short period of time, like a catastrophic container failure, such as a significant chlorine breach due to a train derailment. This type of release will result in a gas cloud that moves across the downwind range, while increasing in size but decreasing in concentration. The concentration of chlorine monitored at any given point downwind will vary over time, depending on a number of factors. A continuous release is characterized by the release of chlorine to the atmosphere over a longer period of time, like a valve failure, rupture, or process fitting failure. This type of release will result in a continuous plume that reaches an equilibrium size and concentration gradient. The concentration of chlorine monitored downwind from the source will be relatively constant for the duration of the release. An intermittent release is characterized by the release of chlorine to the atmosphere for an unpredictable amount of time or frequency. The resulting cloud will be dependent on the length and cycle time of the overall release. One example of this type of release is a pressure relief device cycling due to temperature or volume change, as depicted here. Now, as shown on screen, the area affected by a chlorine release and the duration of the exposure are dependent upon several factors. These are the rate of the release, the duration of the release, the height of the release point. Remember, chlorine is heavier than air and will settle into low areas, the current weather conditions, and the form of chlorine released, as liquid chlorine will increase in volume by 460 times as it becomes a gas. These combined factors are difficult to evaluate in an emergency situation. Chlorine concentrations downwind can vary from barely detectable traces to lethal levels. While the responder most likely will encounter chlorine as a gas, emergency plans should take into account the possibility of the release of liquid chlorine. The location of the leak on the container will determine whether liquid or gas or both will be released to the atmosphere. If liquid chlorine is released from a small puncture or hole, it will most likely instantaneously become a gas. When pressurized liquid or gas is released from a container, the temperature and pressure inside will decrease, and in turn will reduce the release rate. This phenomenon of decreased temperature is due to the changing pressure condition of a breached chlorine vessel. The chlorine in a cylinder container, tank, car, or cargo tank is a liquefied gas under pressure. The temperature of that liquefied gas is cool, but not so cold that the exterior of the container would be cold to the touch. At higher pressures, liquids boil at higher temperatures. At lower pressures, liquids boil at lower temperatures. This is why water boils at lower temperatures at higher elevations above sea level. The atmospheric pressure is lower, so the boiling point is lower. When a chlorine container is punctured or a valve or pressure relief device is broken off, allowing the chlorine to release, at first the chlorine will escape rapidly. As the chlorine is released, the container that was under pressure will now equalize in pressure with the atmosphere. Once the liquid level drains below the puncture point, auto-refrigeration takes place. Auto-refrigeration is the result of chlorine quickly escaping from the container, which causes the chlorine to cool down below its boiling point at the new lower pressure condition. It becomes colder because it is no longer under pressure from being in an enclosed container. Because the chlorine remaining in the container is so cold, a visible frost layer will form on the outside of the container at the liquid level, which is typically the level of the puncture. When this occurs, the rate of release will significantly decrease, although there is still a considerable amount of liquid chlorine remaining in the container. However, any heat source, like water or agitation, like moving the container to a secure location, can cause the remaining liquid chlorine to vaporize and allow more vapor chlorine to escape. Now, as illustrated in this example, escaping liquid chlorine may collect in a pool and may actually form a running stream. Liquid chlorine, upon contact with any heat source, like the air, ground, or water, will boil. Typically, the rate that the liquid becomes a gas will be relatively high initially, and may decrease as the heat source surrounding the chlorine is cooled. The concept of auto-refrigeration will be discussed in further detail in the next video. For now, keep in mind, since water in bulk, as used to fight fires for example, provide the vast heat source for evaporating liquid chlorine, any liquid chlorine falling into water should be assumed to react. For this reason, water should be prevented from coming into contact with the pool of liquid chlorine, and should be prevented from flowing into water drains. In addition, attempts to knock down a chlorine gas cloud with water should not be made. Recall, liquid chlorine will react with any moisture to form hypochlorous acid, a very corrosive substance. In addition, chlorine causes bleach spots on leafy plants because it reacts with the chlorophyll in leaves. Mature leaves are the most susceptible. Usually, the plant itself is not destroyed, but yield or growth rate may be retarded. The effect of chlorine on animal life is similar to exposure consequences in humans. The lowest concentration of chlorine in air, which has been reported to cause death in animals or humans, is listed as 500 parts per million for a duration of 5 minutes. Exposure to lower concentrations for longer durations could also be lethal. First responders should use all their senses when approaching an incident. Be alert to signs around you as indications of high chlorine concentrations. Chlorine is only slightly soluble in water. Aquatic life is fragile and many forms would be adversely affected by chlorine in concentrations well below 1/10 of 1 part per million. Because of this, chlorine is listed as a marine pollutant. Lastly, chlorine does not accumulate in the food chain and is not considered a threat in this regard. This video describes what happens to liquid chlorine in a container when the pressure and temperature change. Specifically, the effect known as auto-refrigeration is discussed. Let's take a closer look. Liquid chlorine is considered a liquefied gas, meaning its normal state at ambient condition is a gas, and therefore has to be compressed or pressurized to form a liquid at ambient temperatures, or it has to be cooled to form a liquid at ambient pressure. This video shows a release of liquid chlorine in an upward direction from a vessel. The liquid chlorine in the vessel starts out at ambient temperature, which equates to a pressure of approximately 70 psi-G or 5 bar G. Once the manway is blown, chlorine gas and liquid mist are released, and the pressure in the tank starts to drop and the chlorine starts to boil. As the chlorine boils, the heat of vaporization is absorbed from the liquid, which causes it to cool. This cooling effect is known as auto-refrigeration. In this infrared video of the same release, the tank can be seen to cool as the chlorine is released. Notice here, however, that the tank is still more than 3/4 full when the chlorine stops projecting from the manway. This is due to the auto-refrigeration effect. Once the liquid in the vessel cools to its boiling point, the liquid stops boiling and the generation of gas stops, thereby essentially stopping the release. At this point, the only gas being generated is due to heat being absorbed by the vessel itself. As seen in this video, the release rate is now very small compared to the initial release. Due to auto-refrigeration and based on the breach location in the container, the amount of chlorine left in the container can vary dramatically. Dikes can be used around liquid chlorine storage containers since the auto-refrigeration effect allows the chlorine to remain liquid at ambient conditions, as seen in this video. Emergency response consideration from this physical behavior is a release from the vapor space of a liquid chlorine container, including rail cars, will result in an initial release of approximately 25% of the liquid chlorine, and then subside due to auto-refrigeration. Once the chlorine and vessel have cooled, plans can be made to transfer the remaining liquid chlorine from the compromised container to another container, or it can be neutralized. Keep in mind though, when transferring the chlorine, it will be corrosive due to contact with moisture in ambient air. In the event of a potential or active chlorine release, one of the primary initial responses for the downwind occupants should be to shelter in place. At the beginning of most incidents, the factual data and information related to the incident is very limited. What is the nature of the incident? Is there a leak or a breach of containment? What is the condition of the vessel or container? If a leak or breach is occurring, how much is currently leaking, and how much has already been released? What is the downwind concentration? And how large is the total downwind area that has been affected? Answers to these questions and others may not be immediately available. Consequently, until an initial evaluation can be made, including obtaining downwind impact information, the most prudent initial guidance is to shelter in place, until the leading official in charge, typically the incident commander, can gain an initial assessment. An initial shelter-in-place action is just that, an immediate action that will place the potentially affected individuals in an environment that offers more protection than being outside without any protection at all. Now, it is important to emphasize, once the shelter-in-place command has been initiated, it should not be an automatic, long-term solution. A shelter-in-place command could be the correct option, but the incident commander and other engaged emergency operations staff should be constantly evaluating the safety and effectiveness of such activities throughout the incident and communicating as appropriate. An organized and directed evacuation via the incident commander is certainly an option. However, in order to make the most informed decision, the incident commander must be engaged, have oversight and control of the operation, and have as much knowledge as possible of what is occurring during the incident. It has long been recommended that the general public, homeowners and renters alike, should be prepared for any type of emergency, including weather-related and natural disasters. An emergency preparedness kit is essential and should include a first aid kit, flashlight, battery-powered radio, extra batteries, a means of communication such as a telephone, cell phone, and/or walkie-talkies, along with the emergency contacts pre-programmed for easy access, non-perishable food, and a 3-day supply of bottled water. In order to be best prepared for a potential chlorine incident, the emergency kit should also contain the following additional items: towels, along with an easily accessible indoor water source like a sink, duct tape, and plastic sheeting. Now, if there is a potential incident and a shelter-in-place command is issued, there are several critical actions that should be taken to increase survivability. Since chlorine is heavier than air and will settle in low-lying areas, you should move to upper floors if possible. Do not go to the basement. In many communities, especially in the tornado-prone areas, the general public has been trained to move to underground shelters or basements in an emergency. This is the exact opposite of what should be done during a chlorine release, as chlorine gas may find its way into basements. So move upstairs or to higher floors if possible. However, do not move to an attic. While attics may be the highest level in a house, they are typically vented in such a manner that they cannot be effectively sealed with duct tape and plastic sheeting. These may include ridge vents, cable vents, and exhaust vents. In order to help prevent the gas cloud from seeping into the structure, quickly close all doors and all windows and seal them with duct tape and plastic sheeting as depicted in this example. From the inside, jam wet towels on the exterior door bottoms and thresholds, and turn off any air conditioning, heating systems, house fans, and bathroom exhaust fans. Now, you may think that running an exhaust fan may help expel any chlorine gas that may have entered the premises, but this could actually create a vacuum or chimney effect, drawing in the chlorine gas. So, for maximum protection, you should go to a windowless room, such as an interior bathroom. It is also critical that you stay connected to first responders, so you need to take a means of communication with you into the safe room: cell phone, telephone, walkie-talkie, or radio. You must remain in place and wait for instructions. You need to wait for rescuers to come to you. You cannot assume it is safe to emerge until instructed to do so. Also, under certain circumstances, sheltering in place can mean remaining inside the vehicle. For example, if an exposure victim drives through a chlorine gas cloud, the vehicle may be the only shelter available. A highly concentrated chlorine gas cloud can disable the engine of a vehicle, preventing escape by driving away. So it is critical that you do not exit the vehicle and attempt to run to safety if you find yourself stranded within a chlorine gas cloud. Survivability is enhanced and risk of injury is reduced if you stay inside your vehicle and perform the following actions. The goal here being to prevent any outside air from entering your vehicle. First, immediately close all windows, including sunroofs. Then, turn off all ventilation systems, such as air conditioning and fans. Some vehicles may have automatic fresh air ventilation systems, so please know how to shut these off or activate the air recirculation feature. Next, alert emergency personnel of your location. If first responders don't know where you are, they can't get to you. Then, turn on your vehicle's radio to find the emergency information. If the engine of your vehicle is disabled from the chlorine gas, the electric system should still operate normally. Finally, stay inside the vehicle until rescue personnel can reach you. Keep in mind, sheltering in place is an effective response if done properly, and it has been shown that simple steps can save lives. A moving crane snagged an overhead pipe connected to a pressurized chlorine vessel, causing it to rupture. 7 employees were exposed to chlorine gas in a number of situations. attempting to repair the damage without donning SCBA, removing SCBA when they thought they were in clear air, continuing the job in the contaminated area, and some were unaware of the chlorine gas cloud. All workers were sent to hospital, but 2 were dead on arrival. Another worker died a few days later, while the remaining workers survived, but unfortunately suffered severe brain damage.
The MGPI facility produces distilled spirits, specialty wheat proteins, and starches. The incident occurred in a section of the plant that uses sodium hypochlorite, or bleach, as well as sulfuric acid. These 2 chemicals, when combined, can form chlorine gas and other chemical compounds. On the morning of the incident, a truck from a chemical distribution company, Harcross Chemicals, arrived at MGPI to complete a routine delivery of sulfuric acid. After reviewing paperwork in the control room, an MGPI facility operator escorted the driver to a locked loading area. There, chemicals are transferred from trucks into the facility through piping, called fill lines, to several large storage tanks in an outdoor tank farm. The MGPI operator unlocked the sulfuric acid fill line for the driver to connect the truck's unloading hose. The operator remembers pointing out the correct fill line to the driver before he returned to his workstation. The driver, however, does not recall hearing the operator identify the fill line. Unknown to the operator, the sodium hypochlorite fill line was also unlocked, and the 2 lines, which were only 18 inches apart, looked similar and were not clearly marked. The driver connected his truck's sulfuric acid hose to the sodium hypochlorite line, and sulfuric acid began flowing inside. He then returned to the cab of his truck. Shortly before 8 a.m., a greenish-yellow gas began flowing from the bulk tank of sodium hypochlorite. The driver noticed the cloud in his truck's side view mirror and attempted to return to the connection area to turn off the flow of sulfuric acid, but the gas overwhelmed him. He then ran to the passenger side of the truck to close a valve that could halt the flow, but he was prevented from doing so by the gas. Instead, he ran away from the cloud and escaped to a separate area of the facility. At about the same time, toxic gases entered the facility control room through the building's ventilation system. MGPI operators preparing for shift change in the control room were immediately overcome by the toxic gas. Because the operators had a practice of locking respirators between shifts, some were unable to access their respirators before evacuating the building. With no other way to stop the flow other than closing manual valves on the fill line or truck, or by triggering one of the truck's emergency shutoffs, the sulfuric acid continued to enter the sodium hypochlorite tank for nearly 45 minutes until emergency responders shut down the flow. Approximately 4,000 gallons of sulfuric acid combined with 5,800 gallons of sodium hypochlorite, causing a large dense cloud containing chlorine gas, which soon drifted off-site. MGPI employees were evacuated from the site, and 11,000 Atchison citizens were advised to either shelter in place or evacuate. Over 140 people, including MGPI employees, emergency responders, the truck driver, and members of the public, sought medical attention, some requiring hospitalization. In its case study on the MGPI incident, the CSB identified several human factors deficiencies, which influenced how the operator and driver interacted with the chemical transfer equipment.
Chemical facility operators and delivery drivers often work directly with chemical transfer equipment for loading and unloading operations. The study of human interactions with process equipment, called human factors, should be carefully considered when identifying hazards, particularly because chemical delivery drivers may not be familiar with the facility's equipment.
For example, at MGPI, the CSB found that the close proximity of the sulfuric acid fill line to the sodium hypochlorite fill line increased the likelihood for workers to make an incorrect connection during chemical unloading. The CSB also discovered that the 2 fill lines looked and functioned identically, using the same type of connections. Lastly, the CSB found that of the 5 fill lines in the unloading area, only 1 was labeled at the point where the hose connected.
A key lesson from our case study is for facilities to evaluate chemical unloading equipment and processes, and implement safeguards to reduce the likelihood of an incident. This should be done while taking into account human factors issues that could impact how facility operators and drivers interact with that equipment.
This can include physically separating fill lines by a discernible distance, selecting hose couplings and fill line connections with unique shapes or colors for each type of chemical, and ensuring that fill lines are properly labeled. Also during its investigation, the CSB found that at the time of the incident, MGPI did not have instrumentation that could automatically shut down the transfer of chemicals from the unloading area in the event of a process deviation. since the only ways to shut down the transfer of sulfuric acid to the sodium hypochlorite tank required human interaction and were located within areas affected by the release. There was no way for workers without proper personal protective gear to stop the flow once it began.
Another key lesson from our case study is for facility management to evaluate their chemical transfer equipment and processes, and where feasible, install alarms and interlocks in the process control system that can shut down the transfer of chemicals in an emergency.
Finally, CSB found that MGPI's procedures were not aligned with their work practices. On the day of the incident, the operator was not present when the transfer hose was connected to the fill line, even though the company's procedures state that operators must verify the connection and that the operator should be the one to open the fill line valve. But the CSB discovered that some operators were not aware of these steps in the procedures and that it was their practice to have drivers open the fill line valve, thinking this would be safer, since drivers wear personal protective equipment in the event of a release.
A third key lesson from our case study is for facilities to work with chemical distributors to conduct a risk assessment and then develop and agree upon procedures for chemical unloading to ensure responsibilities are clearly defined.
As the MGPI incident demonstrates, although unloading operations are relatively simple compared to many of the complex processes taking place at chemical facilities, the consequences can greatly impact workers and surrounding communities due to the large amounts of chemicals transferred during deliveries.
This section provides guidelines, recommended practices, and other information for the safe handling of caustic soda. It represents a compilation of current experience and knowledge drawn from various references and from our company guidelines and training programs. While this video covers the safe handling of caustic soda, it is intended to be supplemental to your employee training programs. Topics to be covered by this training video include basic properties and uses of sodium hydroxide, PPE, safety equipment and first aid, acceptable materials of construction, and spill control and mitigation. Sodium hydroxide, also known as caustic, caustic soda, NaOH, and sodium hydrate, is one of the largest volume chemicals produced and consumed. Caustic plays an important role in the manufacturing of thousands of products we depend on every day, such as soaps and detergents, rayon and other textile products, as well as cellophane paper and cleansers. Common household products such as drain cleaners and oven cleaners usually contain sodium hydroxide. Sodium hydroxide is also a strong inorganic base. It is a clear to cloudy solution. It leaves a white residue when dried. As seen here, caustic will also react sometimes violently with low pH materials. So, mixing strong acids, for instance hydrochloric acid, with caustic will generate large quantities of heat, causing the mixture to splatter. Water also reacts with caustic soda. The reaction will be exothermic, where heat will be released. So, for safety purposes, always add first caustic to water. Never add water to caustic. Caustic solutions are highly corrosive and need to be handled carefully. Contact with eyes or skin can cause severe burns. You may not initially feel caustic when your skin is exposed, so be sure to wash any potentially affected areas. Like most chemicals, caustic can be shipped, stored, and processed safely if proper procedures are followed and personal protective equipment is used. So, always follow your company's PPE procedures. The recommended safety equipment when working around caustic solutions is based on the activity being performed. Your facility may have performed the job safety analysis of specific tasks and may recommend a different level of PPE. Such different levels of PPE are compatible with the purpose and intent of the recommendations in this video. When loading and unloading containers or performing initial line breaks, chemical protective gloves, a full face shield and splash goggles, protective hood or hat, chemical protective boots, and a chemical protective suit should be worn, as illustrated here. Your company's air testing results and policy will dictate whether a respirator is required for any or all of these activities. For material sampling, a face shield, splash goggles, and chemical protective gloves should be worn. For emergency response, chemical protective hood or hat, face shield and splash goggles, chemical protective suit, chemical protective gloves, and chemical protective boots should be worn. In severe cases with spraying caustic and a major leak, SCBA or full face air supply respirator with an auxiliary self-contained air supply should be worn. In less severe cases, such as a leaking valve or a pipeline with no appreciable spraying and/or splashing product, respiratory protection may not be needed. This recommendation is based on the assumption that, unless otherwise determined by the incident commander, the responders to such a sodium hydroxide release will not be exposed to concentrations in excess of 2 mg per cubic meter in any 15-minute period. It is very important that chemical goggles are always worn even when using a face shield. There is a natural tendency to turn the head quickly when sprayed in the face, exposing the side of the face and eyes if not protected. The chemical protective suit should be worn with the jacket buttoned to the neck, sleeves on the outside of rubber gloves, and trouser legs on the outside of chemical-resistant rubber boots. The trouser legs are put on the outside so that if the wearer is splashed with caustic, the caustic will flow down the suit onto the ground and not get trapped inside the boot. This prevents chemical burns to the feet. Where caustic solutions are being sampled and/or handled at temperatures above 120 degrees Fahrenheit, PPE for thermal protection may be necessary, in addition to any chemical-resistant PPE used. So remember to always contact a safety supply provider or a PPE manufacturer for proper PPE selection. Use of protective equipment reduces the possibility for exposure. However, there are other precautions that can be taken to reduce the likelihood of injury should an exposure occur. This will be covered in the next video. Safety showers and eye wash fountains that are readily available, clearly marked and operational in all areas where caustic is being handled, will provide for quick irrigation of skin or eyes exposed to caustic. Safety showers and eye wash fountains should be checked for proper operation before beginning caustic handling activities. Users should also consult the latest ANSI standards Z358.1, which outlines additional criteria in the safe use of safety showers. Topics covered include safe design, placement, water temperature, and inspection procedures. These showers and fountains should have a potable water supply system capable of supplying temperate water. Consideration should be given to providing alarms on safety shower handles to automatically alert other personnel to the emergency. Following precautionary procedures can mean the difference between safety and injury. Sometimes, even a well-trained and well-protected operator can accidentally be exposed to caustic. Proper training and first aid procedures is important when working with caustic solutions. There are 3 important points to remember when dealing with caustic solution exposure. These are speed, water, and medical attention. The sooner caustic is flashed off the skin or out of the eyes with water, the less chance of a chemical burn or permanent vision damage. If your eyes are exposed to a caustic solution, quickly get to an eye wash fountain. Every second counts. Begin flushing your eyes immediately. Once your hands are washed and free of any possible material, use your fingers to hold your eyelids open. This will allow water to flush any caustic solution that is inside the eyelids. Rinse your eyes uninterrupted for at least 15 minutes, and then continue washing until directed to stop by responding medical personnel. If your skin, hair, or clothing is exposed to caustic, quickly get to a safety shower. Keep goggles on and hold them tightly to your face unless the eyes have been also exposed. Goggles prevent caustic on the hair from washing into the eyes. Remove clothing as soon as possible while showering. Forget modesty, you must remove contaminated clothing to prevent injury. After washing your hair, face, and hands, remove the goggles. Continue showering for at least 15 minutes or as specified in your safety data sheet. When personnel have been exposed to caustic solutions, additional medical treatment may be necessary. Never attempt to neutralize the caustic. Neutralization is an exothermic reaction that produces heat and can cause thermal burns as well as chemical burns. In addition, do not apply oils to burns without specific instructions from medical personnel. When necessary, the victim should be moved to a medical facility immediately following prescribed washing. In the case of caustic mists or aerosol inhalation, quickly move the victim into fresh air and consult medical personnel. If caustic is accidentally swallowed, drink large quantities of water and contact the physician, and do not induce vomiting. Much of the information presented in this video is contained in the safety data sheet. Remember, this sheet is available from the sodium hydroxide supplier and should be studied and understood. Keep a copy readily available for review. It is also valuable to send a copy of the SDS with the victim when transported as a quick reference for medical personnel. The guidelines in this section are intended to provide sound engineering practices for the design, fabrication, operation, and maintenance of above-ground caustic storage tanks. The most common material for tank construction is carbon steel for 50% caustic storage tanks maintained below 120 degrees Fahrenheit. Storage tanks constructed of carbon steel can be protected with the application of various lining or coating systems. The success of the liners is typically a function of temperature. There is a wide range of liners in service that include various rubbers, coating systems, metal cladding, and thermoplastic linings. Materials such as PVC, polypropylene, polysulfone, and fluorocarbon resins will normally not be degraded by 50% caustic soda. Plastic tanks and liners can fail if maximum temperatures are exceeded. Therefore, design should take into consideration the maximum process temperature. Many plastics like polyethylene and FRP fabricated storage tanks have been used for small tank storage applications. Here, it is important the tank be designed with sufficient structural strength for the caustic store. It is also important the tank be maintained above caustic freezing temperatures without the use of high-temperature heating devices, which can weaken plastic materials at elevated temperatures. As the temperature increases, caustic becomes more corrosive to many metals. Above 120 degrees Fahrenheit, more corrosive-resistant materials such as alloys of nickel should be considered due to stress corrosion cracking. Stainless steel has been used up to 200 degrees Fahrenheit. Nickel or nickel alloys are used at temperatures above 200 degrees Fahrenheit. Higher temperature storage requires special materials of construction. Caustic is highly reactive with some metals, including aluminum, tin, and zinc, while also generating flammable hydrogen gas. Diluting caustic will generate heat. Therefore, cooling may be required to maintain the integrity of the equipment. Positive mixing devices like agitators or inline mixers should be used to prevent layering of higher caustic concentrations at the bottom of the tanks. Now, the figure that you can see on screen depicts the freezing point of sodium hydroxide as a function of caustic concentration. As seen here, 50% sodium hydroxide solution freezes below 58 degrees Fahrenheit. As a result, 50% caustic should be stored in a heated building or in heated equipment. Keep in mind, frozen caustic may be difficult to return to a liquid state and will require additional heat. Outdoor storage tanks are insulated and heated with steam or electric heaters to keep the caustic from freezing. Self-limiting heat trace and insulation is used to prevent 50% caustic from freezing in outdoor piping system, as in this example. Welded carbon steel piping systems are commonly used. Stainless steel and nickel or nickel alloys are used for higher temperature piping applications. Suitable gasket materials for flange, piping, and equipment include PTFE, EPDM, graphite, or filled PTFE. Ball, plug, butterfly, and gate valves are used in caustic service. Make sure here that the body and sealing materials of the valve are compatible at the system's operating temperature. Keep in mind, aluminum, magnesium, zinc, brass, copper, and tantalum are materials that are attacked by caustic and thus must be avoided. Caustic tanks are normally vented to atmosphere. Never cover a vent used to protect against tank failure due to overpressure or vacuum. Ensure in all cases that the vent size is appropriate for the tank's operation. Liquid caustic can sometimes freeze in and plug tank vents where mist carryover exists. In these instances, ensure tank vents are maintained clear from restrictions due to caustic buildup. In addition, level instrumentation should be provided to prevent overfilling tanks. An overflow pipe directing caustic to a safe location at grade should be provided in the event the tank is overfilled. The capacity of the storage tanks should be at least 1.5 times the size of your largest shipment volume. Always ensure there is enough available space in the storage tank for the tank car or tank truck contents before unloading. It is also recommended that tanks should be located inside diked containment areas that can hold the entire content of the tank. Lastly, spills of caustic should drain to a collection sump to allow for safe collection and disposal. Unloading pipes should be clearly labeled with the proper solution. If you are unloading sodium hydroxide, the pipe should be labeled with UN 1824 or sodium hydroxide solution or caustic soda or any combination of these indicators. It is critically important to prevent the mixing of incompatible chemicals such as acids with caustic solutions. So verify that the chemical name on the bill of lading matches the name of the chemical in the tank and piping system prior to unloading. Finally, proper maintenance of all caustic piping systems is important. All leaks should be isolated and repaired as soon as possible. Now, even when operators attempt to follow approved methods and procedures, spills and releases may occur. The amount of caustic and the circumstances surrounding the release or spill will dictate the reporting requirements. Depending on your location, releases or spills must be reported according to federal, state, provincial, and/or local government regulations. For example, for transportation-related incidents within the United States, Chemtrec should be notified. In Canada, the local provincial authority, usually the local police, must be notified immediately. And in the case of a railway incident, Canutech must also be notified. Chemtrec and Canutech both provide immediate advice for those at the scene of the incident. Chemtrec will also promptly contact the shipper and others as required. Keep in mind the reportable quantity for sodium hydroxide is currently 1,000 pounds as 100% concentration. Specific reporting requirements should be detailed in your facility's spill control or emergency response plan. Documentation of the incident is very important. You should expect to supply the following information. What is the name of the chemical spill? What was the estimated quantity released? What was the time and duration of the release? What are the surroundings into which caustic was released? What are the anticipated acute or chronic health effects? And what are the proper precautions that should be taken? This information can be obtained from the safety data sheet. Keep in mind, containment of a leak is extremely important. So, whenever practical, a dike should be constructed to contain the spill. When the spilled material is unrecoverable, it can be carefully neutralized with a weak acid, such as acetic acid. Caustic should never be flushed to a sanitary sewer or other outlet which connects to waterways or uncontrolled runoff streams. Here, cleanup and waste disposal must conform to applicable permits as well as to current hazardous waste regulations. Lastly, any site handling caustic should have a written emergency response plan in the event a spill or leak occurs. So, if you happen to work at a facility that handles, stores, or produces caustic, then make sure you have access to the latest version of your emergency response plan. Read it and make sure you fully understand it. Acids are considered hazardous because they are corrosive. Acids can react with other substances, evolving large amounts of heat. Their hazard ratings are largely dependent upon their concentrations. Highly concentrated acid solutions are more hazardous because they can react more violently with other chemicals, such as alkalis and bases, and can attack materials such as metals and living tissue more aggressively. The attack on living tissue results in burn-like injuries where the tissue is destroyed. In case of inhalation, remove the person from the exposure, provide respiratory assistance, and seek medical attention immediately. In case of skin and/or eye contact, remove all contaminated clothing, flush with large amounts of water, and seek medical attention immediately. Always check your site's safety data sheet of the particular acid for specific instructions. Water sprays may be used with caution to disperse vapors. Keep in mind, however, the acid may react with water to generate extreme heat, which may ignite surrounding combustible materials. The correct PPE must be worn when handling acids according to their type and concentrations. In general, personal protective clothing must be impervious to acid attacks, while respiratory protection is sometimes necessary if acidic vapors are formed. Always refer to specific safety data sheets for the acidic materials handled at your site. A hydrofluoric acid alkylation unit, as depicted here, had been modified by replacing the liquid caustic neutralizer with a tower containing solid potassium hydroxide. On the day of the incident, the hydrofluoric acid tower was not operating satisfactorily. Although the unit operators were aware of this, they did not know the implications and the corrective actions to be taken, since the operating manuals had not been updated to reflect this process change. A plant upset sent a slug of hydrofluoric acid into the potassium hydroxide tower, which resulted in an exothermic reaction, causing an explosion and fire. The force of the blast threw the side of the tower some 300 feet away. This incident illustrates the dangers of uncontrolled mixing of acids and bases, in this particular case mixing hydrofluoric acid with potassium hydroxide, which are capable of producing sufficient heat of reaction to rupture equipment. To finish off this video, and as a safety note, please remember to always follow the management of change procedure when modifications are made. Never start up a modified plant without the proper manuals and training in place. Liquefied petroleum gas is a colorless, odorless gas when pure, but is commonly used and shipped as a liquefied compressed gas with an odorant added to it. Liquefied petroleum gas is a mixture of primarily propane and butane with smaller amounts of isobutane, butylene, and other hydrocarbons. It is used as a rocket fuel, aerosol propellant, auto fuel, refrigerant for heating, and in cigarette lighters. Liquefied petroleum gas can affect you when inhaled. Contact with liquefied petroleum gas can cause frostbite. Very high levels of liquefied petroleum gas can decrease the amount of oxygen in the air and cause suffocation with symptoms of headache, dizziness, weakness, nausea, vomiting, loss of coordination and judgment, coma, and even death. In addition, liquefied petroleum gas is a flammable gas and a dangerous fire hazard. You can see here the corresponding explosive limits. Before entering a confined space where liquefied petroleum gas is present, check to make sure that sufficient oxygen exists and that an explosive concentration does not exist. In case of eye contact, immediately flush with a large amount of water for at least 15 minutes, lifting upper and lower lids. Remove contact lenses if worn while rinsing, and then seek medical attention. In case of inhalation, remove the person from exposure. Begin rescue breathing if breathing has stopped. And CPR if heart action has stopped. Then transfer promptly to a medical facility. For skin contact, immerse affected part in warm water and seek medical attention. The following recommendations are only guidelines and may not apply to every situation. First, avoid skin contact with liquefied petroleum gas. Wear PPE made from material which cannot be permeated or degraded by this substance. In this regard, safety equipment suppliers and manufacturers can provide recommendations on the most protective glove and clothing material for your specific operation. Keep in mind, however, that in general, safety equipment manufacturers recommend nitrile as a glove material for hydrocarbons, Tychem BR, Trailchem HPS and VPS or the equivalent as protective clothing materials. You can use turnout gear or flash protection if ignition and/or fire is the greatest hazard. Now, when exposure to cold equipment, vapors, or liquid may occur, you should be provided with insulated gloves and special clothing designed to prevent the freezing of body tissues. For eye protection, wear non-vented, impact-resistant goggles when working with fumes, gases, or vapors of LPG. If additional protection is needed for the entire face, use in combination with a face shield. Recall, a face shield should not be used without another type of eye protection. Now, for respiratory protection, first recall, improper use of respirators is dangerous. As a result, respirators should only be used if your employer has implemented a written program that takes into account workplace conditions, requirements for worker training, respirator fit testing, and medical exams. Now, when the potential exists for liquefied petroleum gas exposure over 1000 ppm, use an approved supplied air respirator with a full face piece operated in positive pressure mode. And for increased protection, use in combination with an auxiliary self-contained breathing apparatus or an emergency escape air cylinder. Exposure to 2000 ppm is immediately dangerous to life and health. If the possibility of exposure above 2000 ppm exists, then use an approved self-contained breathing apparatus with a full face piece operated in a positive pressure mode and equipped with an emergency escape air cylinder. Remember, exposure to liquefied petroleum gas is dangerous because it can replace oxygen and lead to suffocation. only an approved self-contained breathing apparatus with a full face piece operated in the positive pressure mode should be used in oxygen-deficient environments. In this video, we'll take a closer look at the dangers of LPG. If LPG leaks, it will evaporate and form a large cloud of gas. The LPG cloud will settle in low spots such as drains or basements, as depicted in this example. And because LPG is highly flammable, this can cause a fire if an ignition source is present. In addition, LPG vapor is heavier than air and may travel a distance to cause a fire or explosion far from the source. In some cases, and under certain circumstances, instead of causing an explosion, it will simply flash back. In this example, the emergency pressure relief system activated. LPG vapors discharged from the process into the atmosphere. It was released horizontally toward an area where many people were working. Soon after, a nearby welding machine ignited the LPG vapor, causing a massive explosion. LPG can also cause cold burns if in contact with the skin. The force of the expanding gas can cause severe injuries. In addition, LPG can act as an asphyxiant if present in high concentrations, as it will displace oxygen. Now, in the event of a fire affecting LPG in storage, particular care is required to prevent the development of conditions which could lead to a BLEVE. In this example, a jet flame shot from a ruptured pipe elbow and heated the bottom of a steel vessel which contained a large amount of LPG, causing it to stretch and thin. The vessel then violently ruptured, causing a large explosion and launching 3 huge fragments into the air. One fragment flew across the river and landed on the river's opposite bank. The other 2 fragments landed inside the facility. The resulting fire and explosion knocked out the control system communication to the refinery water mitigation system. The water mitigation system was a critical safeguard at the refinery, designed to prevent BLEVE and released hydrocarbons from going off-site. The concept of BLEVE will be discussed in a separate video. Okay, now for those of you working in refineries or gas plants, the possibility and consequences of a large LPG leak must be considered. Take a look at the following CFD simulation, illustrating a substantial LPG leak in a chemical plant. In this example, the leaking LPG quickly formed a flammable vapor cloud. The cloud traveled along all directions within the facility. It is important to note here how obstacles, process equipment, structures, and buildings affect the cloud dispersion. The cloud quickly found an ignition source, causing a massive fire. The ignition of the cloud is called unconfined vapor cloud explosion, commonly referred to as UVCE or simply VCE. As in BLEVE, the impact of a VCE may extend well beyond the boundary of the facility and into surrounding areas. The concept of VCE will also be discussed in detail in a separate video. The most effective way to fight an LPG fire is to shut off the LPG supply. However, if this cannot be done, it may be safer to allow the fire to burn itself out, or in other words, to allow the fire to burn until the LPG supply has been exhausted. This recommendation is valid as long as the continuing fire will not result in an escalation of the emergency. Keep in mind and always remember, LPG containers may explode violently in fire, so it is important to keep fire personnel well away. We strongly advise you to watch the video on LPG BLEVE for a better understanding. Now, in the case where the fire cannot be allowed to continue and firefighting efforts should be implemented, dry powder or carbon dioxide fire extinguishers are effective against LPG fires. Water is effective in cooling LPG vessels during a fire and in helping to keep the temperature of tanks and their contents below critical levels. In addition, water spray can be useful in protecting firefighters attempting to close LPG supply valves in heat-affected areas and also in dispersing LPG vapor. The next 2 videos illustrate these concepts. First, keep in mind, if you are required to clean up spills, you must be properly trained and equipped. Never rush to a scene without proper training and proper protective equipment. Now, if liquefied petroleum gas is leaked, take the following steps. First, evacuate personnel. Secure and control entrance to the area. Eliminate ignition sources. Ventilate area of leak to disperse the gas. Stop the flow of gas. If source of leak is a cylinder and the leak cannot be stopped in place, remove the leaking cylinder to a safe place in the open air and repair leak or allow cylinder to empty. Then conduct air monitoring to determine that oxygen levels are above 19.5% and that the lower explosive limit, LEL, is not being exceeded. In all cases, keep liquefied petroleum gas out of confined spaces because of the possibility of an explosion. Prior to working with liquefied petroleum gas, you should and must be trained on its proper handling and storage. The followings are only recommended practices and should not be used as a replacement for your site's guidelines. First, keep in mind, liquefied petroleum gas is not compatible with oxidizing agents such as peroxides, nitrates, chlorine, and fluorine, just to name a few. LPG should be stored in tightly closed containers in a cool, well-ventilated area away from combustibles. Sources of ignition, such as smoking and open flames, are prohibited where liquefied petroleum gas is used, handled, or stored. Use explosion-proof electrical equipment and fittings wherever liquefied petroleum gas is used, handled, manufactured, or stored. Use only non-sparking tools and equipment, especially when opening and closing containers of liquefied petroleum gas. And lastly, metal containers involving the transfer of liquefied petroleum gas should be grounded and bonded. This video summarizes your obligations around LPG safety. If you use, store, handle, or process LPG, then you must have a 2 kg dry chemical fire extinguisher on hand if there is more than 50 kg of LPG present on site. You must have signs showing LPG is present if you have more than 50 kg stored inside or more than 250 kg outdoors. Signs must be located correctly, easy to understand, made from durable materials, and show that LPG is flammable. You must also have a first aid kit available and trained first aiders on site in case of an emergency. For more information on deciding how many trained first aiders you need and what equipment and facilities you need, please refer to your local regulations. In addition, if you have more than 300 kg of LPG in your workplace, you must have an emergency response plan. Make sure you test your plan at least once a year to check if it is effective. Your emergency response plan should include all the potential emergencies that may arise when using LPG, what to do in an emergency, and how to contact emergency services. In addition, make sure that all cylinders are correctly labeled to show that they contain LPG. Make sure that everyone in the workplace has the information, training, instruction, or supervision they need to use LPG safely. This means they need to be aware of the LPG hazards, know what control measures are in place to reduce the risks caused by LPG, know how to safely use, handle, store, and process LPG, and know what to do in case of an emergency. The next couple of videos were developed to cover two important concepts relevant to LPG hazards. These are BLEVE, for boiling liquid expanding vapor explosion, and UVCE for unconfined vapor cloud explosion. We recommend you take the time to watch these videos carefully. The usefulness of these videos is not limited to operating people. There are many useful applications for the maintenance, design, and construction of LPG facilities. Please feel free to share your experience and the knowledge you will gain from these videos with others, since this is one of the most effective means of communicating lessons learned and avoiding incidents in the future. What you have just witnessed is a BLEVE. The term BLEVE stands for boiling liquid expanding vapor explosion. Now, we find liquefied gas tanks everywhere around us. There are approximately 1 million propane storage tanks and 14 million refillable cylinders in use across the US, including in our own backyards. Yet, because of their sturdy construction and safe storage and handling practices, very rarely do we ever have a tank BEVE. A liquefied petroleum gas, or LPG, is a substance that would be a gas at normal atmospheric pressure and temperature, but it is commonly stored and transported as liquid under pressure. The most common liquefied petroleum gas in use is propane. At 20 degrees Celsius, propane is maintained as a liquid as a result of being under pressure of 121 psi or 834 kilopascals. At the critical temperature of 97 degrees Celsius, propane cannot be maintained as a liquid regardless of pressure. And at negative 42 degrees Celsius, propane will remain in a liquid state at atmospheric pressure. If a liquefied petroleum gas container fails, resulting in a sudden loss of containment and a sharp pressure drop, the result can be an explosive release of vapor and boiling liquid. That is a BEVE. The BEVE is a physical explosion with accompanying hazards of blast flying projectiles and a vapor cloud. The substance does not have to be flammable to BEVE. However, if the substance is flammable, such as propane, then the additional hazards of fireball and thermal radiation will most likely occur. A BEVE is a low probability event with high consequences. A BEVE can be devastating, as seen from these videos. Rare though it is, a BEVE is among the greatest danger you can face as a firefighter or emergency responder. Through an accident or a fire, a BEVE can occur with any of these tanks. You could arrive just in time for the blast and have jagged steel projectiles flying at you. BEVEs can happen in places you might expect: a fire in a tank storage area, a tanker truck accident, or a tanker derailment. They can also happen in places you don't expect, or you may not even know there is a tank. For example, barbecue propane tanks unadvisedly stored in basements, sheds, or emergency stairwells. As already demonstrated in this video, a BEVE erupts with a huge fireball and thermal radiation. It sends out a shockwave and sends tank fragments rocketing. The danger zone for projectiles is the greatest. The BEVE of a large tank, as seen here, can propel tank fragments, pipes, and other debris 1,000 meters and more. To begin our discussion, first keep in mind a BEVE happens quickly. The weakening of the tank shell by heat can take just minutes with a severe flame. Tank failure and the BEVE itself occur in a fraction of a second. Let's take a closer look at what can happen. Exactly how does fire cause a tank to BEVE? The fire heats the tank walls rapidly and unevenly, driving up wall temperatures over the vapor space much faster than where the liquid is in contact with the tank shell. As the pressure relief valve cycles to reduce the pressure, gas escapes, lowering the liquid level still more and exposing more vapor area of the tank shell to the rising temperatures. As temperatures soar, the steel walls rapidly lose strength. Wall temperatures quickly reach 400 degrees Celsius over the vapor space, weakening the steel by 30%. Above 600 degrees Celsius, steel strength drops dramatically. By the time the wall reaches 700 degrees Celsius, minutes later, the steel has lost 90% of its strength. Under pressure, the thinned and weakened shell fails, resulting in a catastrophic BEVE. It's amazing how quickly steel weakens at high temperatures. That's why a tank subjected to a strong torch flame can BEVE so quickly, anywhere from 3 to 12 minutes, depending on its size. Now, which size of tank is likely to BEVE sooner, large or small? The answer is small tanks are likely to BEVE sooner. Small tanks empty sooner, heat up faster, and with thinner walls can fail more quickly. With a severe flame heating tank wall temperatures to 700 degrees Celsius, a small 400-liter tank can BEVE in as little as 3 or 4 minutes. A 4,000-liter storage tank can fail in 5 to 7 minutes. And a big 40,000-liter tanker truck can go in 8 to 12 minutes. damaged or corroded tanks may bleve sooner, or if the flame is less severe, they may bleve later by minutes, hours, or even days. The important point to keep in mind is that LPG tanks exposed to fire are dangerous, whatever their size. As you see, a tank can bleve at any time, the moment you arrive, or minutes, hours, or days later. And if and when it goes instantly, with absolutely no warning. So don't expect to see bulging or hear piping noises. So, safety rule 1. If you at all suspect that there is a liquefied gas tank exposed to fire, you never go in immediately and try to attack the fire. Firemen have died doing just that. Instead, you stay way back until you can size up the situation through binoculars. Okay, now what is a reasonable distance for emergency responders to approach in assessing a potential bleve situation? This is a key question. A bleve involving a flammable substance poses 4 main dangers. These are fire, thermal radiation from the fireball, pressure from the blast, and flying projectiles, with the projectiles being the farthest reaching danger of all. First, let's look at the fire hazard. Now, if the release is ignited, there is an immediate fireball. Tests show that when a 400-liter propane tank bleves, the radius of the fireball is about 18 meters. For a 4,000-liter tank, the fireball radius more than doubles to 38 meters. And for a 40,000-liter tank, it more than doubles again to 81 meters. Heat will be radiated in all directions. Safety rule 2 for measuring the danger zone from the thermal radiation is this. Firefighters in protective gear and breathing apparatus should be no closer than 4 times the radius of the fireball, down to a minimum distance of 90 meters. For a 400-liter tank, that translates into a minimum observation distance of 90 meters. For a 4,000-liter tanks, it is 150 meters. And for a 40,000-liter tank, it jumps to 320 meters. The hazard related to pressure changes due to the blast must also be considered. Safety rule 3, the danger zone for blast should extend no further than the minimum observation distance for thermal radiation exposure. However, if the released vapor cloud is not ignited immediately, a delayed ignition could cause a violent explosion, and the blast from this is unpredictable and could be far-reaching. Now, it is important to keep in mind that in case of a bleve, the furthest reaching danger by far is flying projectiles. Even at the minimum observation distance to avoid excessive radiation, you can still be exposed to this hazard. Several tests of induced bleves of 400-liter tanks scattered projectiles over a wide area, as depicted here. Note the location of primary fragments, including the tank ends and other large pieces. Secondary fragments such as piping, attachments, and any other objects near the tank are also a danger. Note that some large projectiles fell far beyond the suggested 90-meter minimum observation distance for a 400-liter tank. As a consequence of this, for your own safety, keep in mind that the best point for observation is beyond the minimum distance in order to avoid excessive radiation, with face on to the side of the tank and with the wind at your back, as seen here. And even here, some fragments may fall beyond the observation point. To sum up, even for a 400-liter tank, the minimum observation distance for firefighters in protective gear is the minimum distance of 90 meters. This is a suggested minimum distance to avoid extreme danger from the blast and thermal radiation. However, remember, at this distance, you can still be hit by projectiles. For public protection, consider evacuation distances of about 22 times the fireball radius. 400 meters for a 400-liter tank, 800 meters for a 4,000-liter tank, and 1,800 meters for 40,000-liter tank. Now, take the time and think about these distances. Even for the 400-liter tank, the minimum observation distance is 90 meters. This is well beyond the range of your hoses, and even at 90 meters, you could still be hit by a projectile. These distances provide you with some measure of the risks involved, and you should take these into account when you're faced with responding to fire where liquefied petroleum gas is present. Now, is there any safe way to approach a fire-impinged tank? Definitely not. As we've said, the best position to observe a damaged or fire-impinged tank is upwind and face on to the side of the tank in order to reduce the danger from projectiles and avoid any escaping vapor cloud. But always keep your distance. Observing with the wind at your back can give you a false sense of security, because wind can blow the fire to the other side of the tank, so you may not see it contacting the tank. The tank may burst away from you, but the projectiles can still come in your direction. It is unpredictable. The fact is, there is no safe way to approach a fire-impinged tank, even in protective gear. If you're looking at a big tank, a tank truck or a tank car, even a fire truck won't be a big enough shield to protect you. Now, is the situation under control if the pressure relief valve is releasing gas? The answer is no. LPG tanks can and do fail even when the PRV is trying to relieve excess pressure. PRVs don't prevent the tank from weakening with heat. In fact, by lowering the liquid level in the tank, they can contribute to the weakening of the steel, since they expose more overhead tank shell to the naked flame, as depicted in this example. However, PRVs releasing pressure do warn us that something is happening. But having said that, keep in mind, with severe fire exposure, a bleve can occur whether the PRV is open, closed, or cycling. If the PRV closes, as seen here, does that mean that the tank is empty? The answer is no. Remember, even with the PRV closed, there still is pressure in the tank. In rare cases, the PRV could be stuck and the tank pressure could be very high. Now, if the flame is contacting only the bottom of the tank, where the tank shell temperature is kept lower by the liquid, can the tank still bleve? The answer is yes, but it may take longer to happen. With a fire on the tank, the situation is always changing. As the fire heats the liquid, the pressure increases. The PRV opens to relieve the pressure, and the PRV slowly empties the tank. It is doing its job of relieving pressure, but it is also lowering the liquid level in the tank. This can bring flame over the vapor area and possibly cause the tank to fail, resulting in a bleve. Okay, now is there a difference if the tank is rolled over on its side? The answer is yes. If a tank is rolled over on its side, the PRV will be venting liquid, as seen here. As a result, the tank empties more quickly, so that with a severe fire, it can bleve sooner. Also, the escaping liquid immediately vaporizes and will ignite on contact with flame or spread in cloud and then results in a vapor cloud explosion. Okay, next, can a thermally protected tank bleve? Yes, but it is generally much less likely to. However, if the fire is severe enough, or if the insulation, depicted here in green, has damaged, the tank wall can be directly exposed to fire. The tank wall can then heat up unevenly and could bleve. The safety message is simple. With a fire-impinged tank, you keep your distance, a long, long distance. Whether the tank is large, small, upright, or on its side, insulated or not, whether the PRV is open, closed, or cycling, you can't approach close enough to get water on the tank without getting well into the danger zone. So, with a fire-impinged tank, let me say this once again, you keep your distance, a long, long distance. But suppose now that the fire has not reached the tank yet. The flames are getting closer and closer, and you want to protect the tank. So what would you do? Think about it. You can keep the tank cool with water if you can approach close enough to get water on it, and if you have enough water. But if your fire truck is your only water source, you may not have enough water. A truck carrying 4,500 liters of water will only provide enough water to keep the tank cool for about 2 to a maximum of 20 minutes, depending on the flow of water needed and the size of the tank. Now, water spray can be effective in keeping a tank cool if the water is applied immediately. However, it requires high volumes of water. For a small 400-liter tank, you need 200 liters a minute. The 4,000-liter tank requires 700 liters per minute, and a tanker truck demands 2,000 liters a minute. Just as important, the available water supply should be sufficient to maintain required volume until the incident is over. Remember, these water volumes are only sufficient to keep steel temperatures at an acceptable level, provided there is no direct flame impingement on the tank. Also, the water must be applied uniformly to cool the tank surface evenly, or you could cause the tank to fail. To get water on a tank, you've got to get your equipment within the maximum effective spray range of 15 to 30 meters. If your water runs out, you'll be deep in the danger zone, as the fire starts to heat up the tank with maybe just a few minutes to get out of there. Conclusion: unless you have an adequate supply of water, don't even try to protect a tank from approaching flame. You could end up in a trap. If you see steam rising from the tank surface, get out and get out fast. Now, when is the danger of a BLEVE over? For a severely weakened tank, the danger is only over when the fire is out and the tank is exhausted of gas. If you see a hole in the tank, you'll know there is no pressure, but then you must watch for gas vapors. So even after the fire is out, avoid approaching the tank and seek expert advice on how to eliminate the remaining hazard. Now, one final thing about BLEVEs. You don't need a fire to have one. Whatever causes a tank to be severely damaged, such as impact fatigue, severe corrosion, or a rise in temperature, can result in a BLEVE. A damaged tanker overturned on the highway and left in the sun for hours could blow without any fire. To prevent the possibility, the tank should be emptied or kept cool before pressures and temperatures can rise in the tank. The best way to deal with a potential BLEVE situation is to try to prepare for it, and hence prevent it from happening. In order to do so, survey sites within your area that store, handle, or use liquefied petroleum gas. Familiarize yourself with their safety equipment and water capacities. Time how long it takes to get to any BLEVE potential sites, and assess what you might be able to do in the event of a fire. Pre-plan your strategies based on knowing your capability for dealing with a potential BLEVE. Know the size and location of tanks in your area, water supply volume, duration, capacities of relay units, capacities of pumps, available personnel, and backup. Plan observation points for each potential BLEVE site based on the minimum distances we have discussed previously. Assess all areas of risk and develop evacuation plans. Familiarize yourself with tank codes and regulations and report any contraventions. Know how to contact experts in liquefied gases at your facility. Finally, keep your eyes open for dangerous tank installations in your area and report them. Any storage or fuel tank placed too close to a building is dangerous and probably illegal. The fact is, your very best response to a potential BLEVE situation is to prevent one from ever happening. Remember, caution is the watchword, prevention is the key. The most dangerous and destructive explosion in the chemical process industries are unconfined vapor cloud explosions. These explosions occur in a sequence of steps. First, sudden release of a large quantity of flammable vapor. Typically, this occurs when a vessel containing a superheated and pressurized liquid ruptures. Then, dispersion of the vapor throughout the plant site while mixing with air. And next, ignition of the resulting vapor cloud, leading to a fire and/or explosion. The accident at Flixborough, England, is a classic example of a VCE. A sudden failure of a 20-inch cyclohexane pipe between reactors led to vaporization of an estimated 30 tons of cyclohexane. The vapor cloud dispersed throughout the plant site and was later ignited by an unknown source 45 seconds after the release. The entire plant site was leveled and 28 people were killed. Now, it is important to note that VCEs have increased in number because of an increase in inventories of flammable materials used in process plants and because of operations under more severe conditions. Any process containing quantities of liquefied gases, volatile superheated liquid, or high-pressure gases is considered a good candidate for a VCE. VCEs are difficult to characterize, primarily because of the large number of parameters needed to describe an event. VCE accidents occur under uncontrolled circumstances, Data collected from real events are mostly unreliable and difficult to compare. Some of the parameters that affect VCE behavior are quantity of material released, fraction of material vaporized, probability of ignition of the cloud, distance traveled by the cloud before ignition, time delay before ignition of the vapor cloud, probability of explosion rather than fire, efficiency of explosion if it occur, and location of ignition source with respect to the release point. All of these parameters are discussed in detail in our separate course, Chemical Process Safety Calculations. Now, keep in mind, qualitative studies have shown that the ignition probability increases as the size of the vapor cloud increases. The vapor cloud fires are more common than explosions. The explosion efficiency is usually small, roughly 2% of the combustion energy is converted into a blast wave. And lastly, turbulent mixing of vapor and air and ignition of the cloud at a point remote from the release increases the impact of the explosion. Now, of course, from a safety standpoint, the best approach is to prevent the release of material in the first place. Keep in mind and always remember, a large cloud of combustible material is dangerous and almost impossible to control, despite any safety systems installed to prevent ignition. Recall, even though ignition sources are identifiable, they are uncontrollable. Now, methods that are used to prevent VCEs include keeping low inventories of volatile flammable materials. This is part of the inherently safer design philosophy. Using process conditions that minimize flashing if a vessel or pipeline is ruptured. Using analyzers to detect leaks at low concentrations, and installing automated block valves to shut down systems while the spill is in the incipient stage of development. The next couple of videos show some vapor cloud explosions that recently occurred in the chemical industry. Please watch these videos carefully and note the devastating effects of these VCEs.